Hey everyone, welcome. I'm Somil and this is FastAPI for GenAI backends. By the end of this course, you're going to know exactly how to take any AI application you have built and turn into a production-ready API. Before we get into the technical stuff, I want to start with a story that a lot of you might actually relate to. Meet Karan. He's 24, a CS grad, and he has been putting in the work. He built RAG pipelines, connected LLMs to custom data, and even shipped a few chatbot prototypes. By most measures, Karan is well ahead of his peers. He walks into an interview feeling genuinely prepared, and then something unexpected happens. The interviewer looks at Karan's project, nods, and then asks, "This is great, but how would you actually serve this in production? Can you expose it as an API, handle concurrent requests, add authentication?" Karan knows the AI side cold, but the deployment layer, the serving layer, the part that makes an AI app a real product, that's the gap. And it cost him the offer. This course exists to close that gap. So what exactly will you walk away with? By the end of this course, you will be able to design and build production-grade APIs for your AI application, serve RAG system and LLM workflows through clean typed endpoints, apply security and testing practices that makes your APIs interview and production worthy, and deploy them to the cloud. Everything Karan he wished he knew, you will have them covered end to end. You're not just going to learn the concepts, you're going to build two real projects. The first is RAG API for podcast transcripts. You will build endpoints for ingestion, retrieval, and streaming answers. The second is a text to SQL agentic API, where user asks questions in plain English and your service generate and execute save SQL queries. You're not just going to learn the concepts, you're going to build two real projects. The first is RAG API for podcast transcript. You will build endpoints for ingestion, retrieval, and streaming answer. The second is a text to SQL agentic API, where user asks question in plain English and your service generates and executes save SQL queries and return the answer in the natural language. Both projects are the kind of thing you can walk into an interview with and confidently talk through end to end. Here's how the course is structured. We start with the foundations, what FastAPI is, how asyncs work, and your first running app. Then we go deeper into request and response patterns, application architecture, security, and testing. From there, we move into persistent and state management, and then you build both projects. We close with production deployment. Every module builds on the last, and Karan is right there with you the whole way. That's your overview. You know exactly what this course is going to give you, what you will build, and how it will connect. In the next video, we are going to look at FastAPI properly, what it is, how it compares to other frameworks, and why it became the go-to choice for Python team building GenAI backends. I'll see you there. Welcome back. In the last video, we met Karan and understood the gap this course is going to close. Now let's get into the first real question. What exactly is FastAPI and why it is the right choice for building GenAI backends? By the end of this video, you will have a clear mental model of where FastAPI sits, what makes it different, and why it became the go-to framework for Python teams shipping AI products. After that interview, Karan goes home and thinks. He didn't fail because he couldn't build AI apps. He failed because he didn't know how to expose them, serve them, or harden them for real use. That's exactly where FastAPI comes in. It's the layer between your AI logic and the outside world, and that's what we are going to understand properly right now. FastAPI is a modern Python web framework, purpose-built for creating APIs. It sits on the top of two very solid libraries. Starlet handles everything related to the web, routing, middleware, and async support. Pydantic handles data validation and type enforcement. Together, they give FastAPI a foundation that is both fast and reliable. And when we say fast, we mean it literally. FastAPI benchmarks amongst the fastest Python frameworks available, comparable to Node.js and Go in many scenarios. To understand where FastAPI fits, it helps to place it next to Flask and Django. Flask is lightweight and flexible, but requires you to wire up validation, async, and docs yourself. Django is powerful for full-stack web apps, but brings a lot of overhead for pure API work. FastAPI was designed specifically for API-first, async-first use cases. For GenAI backends, that distinction matters a lot. You're not serving HTML pages. You're handling structured input, calling LLMs, querying vector databases, and returning typed responses. FastAPI is built exactly for that. One of the most important things FastAPI brings to AI backends is typed validation via Pydantic. Think about what your endpoints receive: prompts, conversation histories, retrieval setting, model parameters. These are structured complex inputs. If something is malformed, you want to catch it at the API boundary, not deep inside your model logic. Pydantic does that automatically. You define your input and output shapes as Python classes, and FastAPI validates every request against them. No extra code, no manual checks. Every FastAPI application comes with interactive documentation out of the box. Hit/docs in your browser and you get a fully functional Swagger UI, where you can read, test, and explore every endpoint. Hit/redoc for a cleaner reading view. The best part, this documentation is generated directly from your code. When you add a new endpoint or change a model, the docs update automatically. For teams building AI APIs that other developers or frontend will consume, this is a productive win. This is a huge productivity win. FastAPI is built async first, and for GenAI backends, that is not optional, it is essential. Think about what happens when a user sends a query to your RAG API. Your server calls an embedding model, queries a vector database, then calls an LLM. Each of those steps can take seconds. In synchronous server, every other request is blocked while that's happening. In an async FastAPI server, while one request is waiting on an LLM's response, your server is already handling the request. You define async endpoints with just one keyword, async def, and that's it. FastAPI is built async first, and for GenAI backends, that is not optional, it is essential. Think about what happens when a user sends a query to your RAG API. Your server calls an embedding model, queries a vector database, then calls an LLM. Each of those steps can take seconds. In a synchronous server, every other request is blocked while that's happening. In an async FastAPI server, while one request is waiting on LLM response, your server is already handling the next request. You define async endpoints with just one keyword, async def, and that's it. Now, let's bring it all together. FastAPI fits GenAI backends for four concrete reasons. First, type validation means your API contracts are clean and enforced automatically. Second, async support means your server stays responsive even under slow LLM and retrieval calls. Third, it's a Python native, which means your LangChain, LlamaIndex, OpenAI, or any other AI library plugs in without friction. This isn't workaround. FastAPI is the right tool for this job. And fourth, automatic doc means your API is always self-describing and testable without extra effort. To wrap up, FastAPI is a modern async-first Python framework built on Starlit and Pydantic. It gives you type validation, automatic documentation, and native async support out of the box. For GenAI backends specifically, it is the cleanest fit available in the Python ecosystem. And now, Karan is starting to see what he was missing. In the next video, we are going to go one level deeper and cover the Python typing concepts you need before we start writing real FastAPI code. See you there. Welcome back. Before we write a single FastAPI endpoint, there is one concept we need to get solid on: Python type hints. This isn't a detour. FastAPI is built entirely around Python's type system. The moment you understand how typing works, everything in FastAPI, from request validation to automatic docs to response filtering, will make complete sense. Let's get into it. Here's the thing about Karan's situation. He knew how to call an LLM, build a retrieval pipeline, and chain together prompts. But when it came to exposing that as an API, there was no structure, no contract, no way for the framework to know what was coming in or what should go out. FastAPI fixes that through Python type hint system. Once your code is typed, FastAPI can validate every request, reject bad inputs, and generate documentation, all automatically. Types are the foundation everything else is built on. Type hint are Python's way of letting you declare what type a variable, parameter, or written value should be. The syntax is simple. Add a colon after the name and specify the type. Now here's something important to understand. Python itself does not enforce these at runtime. If you pass an integer where a string is expected, Python won't complain. But FastAPI and Pydantic do enforce them. That's the critical distinction. When you use type hint inside FastAPI, they become real constraints that protect your API. When you use type hint inside FastAPI, they become real constraints that protect your API. Now let's start with the basics. Python has four core primitive types you will use constantly in FastAPI. String are for text, integer for whole numbers, float for decimal, and boolean for true or false values. These maps directly to what you will define in your API requests and response models. A username is a string, A page number is an integer. A confidence score for your model is a floating number. A flag for whether streaming is enabled is a boolean. These are simple, but you will use all four constantly. Beyond primitives, you will regularly work with collections, a list of messages in a chat history, a dictionary of metadata, a batch of inputs. Python lets you type these properly using generics. List string means a list where every item must be a string. Dictionary string comma float means a dictionary with string key and float values. This level of specificity matters in FastAPI because it tells Pydantic exactly what to validate inside your collection, not just at the top level. Not every field in your API will be required. A user might send a query without a system prompt. A request might omit certain configuration values. For these cases, you use optional. Optional string means the value is either a string or none. In modern Python 3.10 and above, you can write this as string union none directly. Union goes one step further and lets you accept multiple types of single field. In practice, optional is something you will use in almost every Pydantic model you write in this course. So you know FastAPI is built async first, and for GenAI backends that is not optional, it is essential. Think about what happens a user sends a query to your RAG API. Your server calls an embedding model, queries a vector database, and then calls an LLM. Each of those steps can take seconds. In synchronous servers, every other request is blocked while that's happening. In an async FastAPI server, while one request is waiting on an LLM response, your server is already handling the next request. You define async endpoints with just one keyword, async def, and that's it. And here's where everything comes together. When your FastAPI application starts, it reads every endpoint function you have defined. It inspects the type hint of each parameter and return type. And from that inspection alone, it does three things. It validates every incoming request against those types. It rejects anything that doesn't match with a clear structured error. And it generates your entire API documentation. You don't write a schema file separately. You don't configure validation separately. You type Python code in the single source of truth for all of it. And now let's recap. Type hint lets you declare what your code expects and return. Python itself won't enforce them, but FastAPI and Pydantic will. We covered primitive types like collection types, optional, and union, and how typed function signatures map directly to FastAPI endpoints. Most importantly, you now know that in FastAPI, your type hint are not just documentation for other developers. They are the mechanism that drives validation, error handling, and API document generation. In the next video, we are going to cover the async mental model, so you understand exactly what async does and doesn't do before we start building endpoints. See you there. Welcome back. In this video, we are going to talk about async. Now, async is one of those things that sounds complicated but really isn't once you say it the right way. A lot of developer thinks async just means faster. That's not quite right. By the end of this video, you will know exactly what async does, where it actually helps, and where it doesn't. Let's start. So, when Karan saw the fast API and async first, he thought, great, I will use async everywhere and everything will be faster. That's very common assumption, but it's not how async works. Async helps in some situation that does nothing useful in others. If you use it the wrong place, you just make your code more complex for no gain. So let's build the right picture from the start. Here's the simplest way to think about async. Look at the chef on the screen. He put a dish in the oven. He has two choices, stand in front of it doing nothing or go chop vegetables while it bakes. Async is the second chef. While your code is waiting for a response from an external service, it goes and handles something else instead of sitting idle. That's really all async is. Not magic, just not wasting wait time. Now here's the key question. When does async actually help? It comes down to the type of work your code is doing. Input-output bound work means your code sends a request and waits for something to come back. CPU bound work means your processor is busy running calculation. Async helps when your code is waiting. It does nothing useful when your processor is already busy. Let's look at both with examples. Input-output bound work is when your code is just waiting. You call the OpenAI API and wait for the response. You query your vector database and wait for results. You fetch conversation history from a database and wait for it to load. These things can take anywhere from a few hundred milliseconds to several seconds. During all that waiting, an async server doesn't just sit there. It goes and handles another incoming request. That's where you get real performance improvement. Now, look at the CPU bound diagram. Requests come in, they hit your server, and the server sends them straight to the CPU for active computation. There's no waiting involved. The CPU is busy the whole time. Notice the queue building up at the bottom? That's what happens when the CPU can't keep up. Async won't help here because there's nothing to wait on. The right solution is separate worker processes that can handle computation in parallel. Now, let's see this in a real scenario. A user sends a query to your RAG API. Your server calls an embedding API. That's waiting. Then queries the vector database. More waiting. Then calls the LLM. Waiting again. In a regular server, every other user is blocked during all of this. In an async server, while step 1 is waiting for the embedding API, the server is already picking up the next request. For a production API with many users hitting at once, this makes a huge difference. Here's the simple rule. Ask yourself, is my code waiting for something or is it actively computing? If it's waiting, use async def. If it's computing, use a regular function or a separate worker. And one thing to never do, don't put heavy CPU work inside an async function. It will block your server and make things worse, not better. That one question, waiting or computing, is all you need to make the right call every time. To wrap up, async means don't waste time waiting. Go do something else instead. It helps when your code is waiting on external responses, which is most of what GenAI backend does. It doesn't help when your processor is busy computing. Remember the rule, waiting means async def, computing means regular def or a worker. Next up, we get practical. We will set up the environment, install FastAPI and write your first very running endpoint. Next up, we get practical. We will set up environment, install FastAPI and write your very first running endpoint. Welcome back. This is where we stop talking and start building. In this video, we will set up everything you need to run FastAPI on your machine and write your very first endpoint. By the end, you will have a running FastAPI app with an interactive dock open in your browser. Let's get started. Before we touch any code, let me show you what we are going to set up. Three things. First, a virtual environment so our project dependencies stay isolated. Second, FastAPI installed with its standard extras, which includes everything we need to run and test locally. And third, a minimal project with one endpoint that we can actually run and see working. Simple and clean. Let's go step by step. So, before installing anything, make sure you have Python 3.10 or above. You can check by running Python version in your terminal. If you are on an older version, head to python.org and grab the latest one. For code editor, we recommend VS Code. It's free and works great with Python. And you will need a terminal, which is built right into VS Code. For code editor, we recommend VS Code. It's free and works great with Python. And you will need a terminal, which is built right into VS Code if you are using it. That's all you need before we move on. Now, the first thing we do is create a virtual environment. Think of it as a clean, isolated space for your project packages. Without it, if you install FastAPI for this project, it shares the space with every other Python project on your machine, and that causes conflicts down the line. So now let's head to our VS Code terminal. Here first we will check our Python version. So Python version, and it's 3.13, so we are good. And now using conda, I'll create a virtual environment. So I'll write the command conda create fast python equals to 3.11. I'll hit enter. So right now it is creating my virtual environment. I'll say yes and we are good to go. So now I'll activate my virtual environment using the command conda activate fast. Okay, so now we are in our virtual environment. So now let's install FastAPI. So I'll write the command pip install FastAPI uvcon. So it's installing the dependencies and now it's all done. Now I'll create a file name main.py and here we will create our first endpoint. So let's start by importing FastAPI. So from FastAPI import FastAPI, and now we will create the app and then a demo endpoint which will return hello world. And I'll save this file and on the terminal I'll go and write the command uvcon main. So now I have saved my endpoint and now I will run it on the terminal. So using the command uvcon main app reload. Let enter. And as you can see, my app is running. So I'll open this URL And when I will click on this URL, you can see the message written hello world. So let's hop on to our, so now let's hop on to our link, and here you can see it is written hello world. So you have successfully made your first endpoint. And now if you want to look at the documentation of this endpoint, you have to just add /doc. And now if you want to see the documentation for this endpoint, you just have to add /docs in the URL. So as you can see, here's the documentation. We got a get method here. Here's our get method here with everything, code, description, and parameters are not there right now, but yes, if you give parameters, they will be visible here. And if you want to see a better UI, you can just add redoc instead of doc. And here you will get a better UI here where you can check your endpoints. And that's it. That's your first FastAPI app up and running. You have set up a clean environment, installed FastAPI, written your first endpoint, and seen the automatic doc in action. In the next video, we are going to explore those docs properly, Swagger UI, redoc, and the OpenAI schema that FastAPI generates for you. See you there. Welcome back. In the last video, you wrote your first FastAPI app and ran it locally. You may have noticed that FastAPI gave you a /doc URL without you doing anything extra. In this video, we are going to understand exactly what that is, how it works, and why it matters for anyone building AI APIs. Let's get into it. Before we look at the docs, let's understand what's powering them. Look at the diagram. On the left, you have your Python code. FastAPI reads that code, specifically your type hints and pydantic models, and generates an open API schema automatically. That schema then powers three things: your interactive docs, your testing interface, and client code generation. You write Python and FastAPI does the rest. Now, the first place to go is /doc. Open your browser, open your app link in it, and add /docs at the end. While you're running, you will see a Swagger UI, a clean interface that lists every endpoint in your application. Click on any endpoint, and it expands to show you exactly what input it expects and what it will return. Hit the try it out button and you can send a real request right from your browser. No postman or curl needed. And remember, you don't write any of this. FastAPI generated it entirely from your code. Now, FastAPI also gives you a second docs interface /redoc. Redoc has a cleaner, more readable layout. It is not built for testing endpoints interactively. It is built for reading and understanding your API at a glance. If you are sharing your API documentation with a front-end team or a client, redoc is a better view to send to them. Think of it this way. Use docs when you are developing and testing. Use redoc when you are communicating and sharing. There is one more URL worth knowing, /openapi.json. Visit it and you will see the raw schema FastAPI is generating behind the scenes. Look at the code on the right. It is structured JSON file that describe your entire API, every path, every request body, every response model, and the status code. You probably won't read this manually very often, but external tools use it to auto-generate API clients, run contract tests, and integrate with API gateways. It is also exactly what Swagger UI and redoc are reading to render what you see on /docs and /redoc. So how does FastAPI do all of this? It comes back to what we covered in the typing video. When your app starts, FastAPI inspects every endpoint function. It reads the type hint on the parameters, the pydantic models you have defined, and the return types. From all of that, it builds the open API schema automatically. There is no separate documentation file to write, no schema to maintain, no config to update. You change your code, the docs change with it. That's one of the biggest productivity wins FastAPI gives you, especially as your own API grows. To wrap up Module 1, FastAPI gives you three documentation interfaces out of the box. /docs for interactive testing, /redoc for clean reading, /openapi.json for the raw schema. All of it is generated automatically from your typed Python code. No extra work required. Karan now has the foundation he was missing. He understands the framework, the tooling, the async model. Now, in Module 2, we get into real building blocks: how to design endpoints, handle request bodies, manage responses, and deal with errors. See you there. Welcome to Module 2. In Module 1, you got FastAPI running, understood the async model, and saw how automatic doc works. Now we go deeper. Before we write real endpoints, we need to understand how to design them well. That starts with REST. In this video, we will cover what REST is, how routes and HTTP verb works, and when REST is the right mental model for AI APIs. Now, Karan got his first app running. He saw the docs, hit his Hello World endpoint, and felt good. But now he's starting at a blank file, thinking about his actual project. How should I name my routes? When do I use post versus get? What does a well-designed API even look like? These are the questions we are going to answer right now, and it starts with understanding REST. REST stands for Representational State Transfer. Don't worry about the name. What matters is the idea behind it. REST is a set of design principles that tells you how to structure your API. The core idea is simple. Build your API around resources. A resources is any piece of data your API manages. In an AI backend, that could be a user, a document you have ingested, a chat session, or a query result. REST says give each resource a clear URL and use standard HTTP verb to act on it. That's the foundation. A route is the URL that points to a resource. The naming convention is straightforward. Use the plural noun for the collection, like /documents refers to all documents. Add an ID to refer a specific one, like /document42 is document number 42. You can also nest routes for related resources. For example, /sessions/5/messages refers to all messages inside session 5. One rule to remember, route should be nouns, not verbs. The verb comes from the HTTP method, not the URL. So it's /document, not /get documents or /fetch document. Now, the HTTP verb tells your API what action to perform on the resource. Get is for reading. You are fetching data, not changing anything. Post is for creating something new. Put replaces an existing resource entirely. Patch updates only part of it. Delete removes it. Together, the route and the verb fully describe the action. Get/document means fetch all documents. Post/document means create a new document. Delete/document/42 means remove document 42. Clean, consistent, and predictable. REST is a great mental model for most of your AI backend, but not all of it. It works really well when you are managing resources like ingesting documents, handling sessions, and managing users. These map cleanly to routes and verbs. But REST starts to feel awkward when you are dealing with streaming LLM responses, long-running background jobs, or multi-step agentic workflows. These don't fit neatly into the request-response model REST assumes. The good news is that FastAPI handles all of these cases well. We will cover streaming in Module 6 and background task in Module 5. For now, REST gives you a solid foundation for the majority of your endpoints. To wrap up, REST is a design style, not a strict rule. The core idea is to build your API around resources. Use clear noun-based routes and let HTTP verb define the action. For most of what you will build in this course, REST gives you a clean, predictable structure. In the next video, we will go one level deeper. Path parameters and query parameters. These let you pass data through your routes and filter results. And they are something you will use in almost every endpoint you write. See you there. Welcome back. In the last video, we covered how to design clean REST endpoints. Now we go one level deeper. Most real endpoints aren't static. They need to accept dynamic values, a document ID, a search query, or a page number. In this video, you will learn two ways to pass data through your routes: path parameter and query parameters. By the end, you will know exactly when to use each one and how FastAPI validates them for you automatically. Now, think about what a static route looks like. If you write /document/42, that endpoint only ever returns document 42. It works for one case and nothing else. In a real API, you need to fetch any document by its ID, filter a list by keyword, or paginate results. You need your routes to accept dynamic values. FastAPI gives you two clean ways to do that: path parameter and query parameters. A path parameter is a variable that lives directly inside your route URL. You define it using curly braces. So, /document/curly braces document ID means whatever value comes in that position of the URL becomes the document ID variable. Look at the code on the screen. You declare the parameter in the route string and then add it as a typed argument to your function. FastAPI automatically extracts the value from the URL and validates it against the type you declared. If someone hit /document/42, document ID gets the value 42. If they pass something that isn't an integer, FastAPI rejects it immediately with a clear error. Now, query parameters work differently. They are not part of the route itself. They come after the question mark in the URL. In FastAPI, you define them as regular function arguments that don't appear in the route string. Look at the example. The slash document route has three query parameters: keyword, page, and limit. All three have default values, which makes them optional. A caller can hit slash document and get the first page of everything, or hit slash document keyword equals to fast API and page equals to 2 to filter and paginate. Fast API parse and validate all of it automatically. Now, here's the simple rule. Use a path parameter when you are identifying a specific resource. You need that value. The endpoint doesn't make sense without it. Use a query parameter when you are filtering or configuring the response. It's optional and has sensible default. Slash document slash 42 uses a path parameter because you are asking for one specific document. Slash documents keywords equals to rack uses a query parameter because you are searching a collection with an optional filter. Path equals identity. Query equals option. Keep that in mind and you will make the right call every time. So, here's where FastAPI saves you a lot of work. Both path and query parameter are validated automatically using type hint. If document ID is declared as int and someone passes the string ABC, FastAPI immediately returns a 422 error with a clear message explaining what went wrong. You don't write any validation logic yourself. The type hint is the rule. This applies to every type: int, float, bool, string, and because this validation happens at the API boundary, bad data never reaches your actual business logic. Current's API is already safer just by using types. To wrap up, path parameters go inside the route and identify a specific resource. Query parameters comes after the question mark and are used for filtering and optional configuration. FastAPI validates both automatically from your type hint. No extra code needed. In the next video, we move to request bodies. When you need to send structured data like a prompt, a config object, or a chat message, query parameters aren't enough. That's where Pydantic models comes in. See you there. Welcome back. So far we have used path and query parameters to pass data in our endpoints. But what happens when the data gets more complex? A user prompt, a chat history, a retrieval config. These can't fit neatly into a URL. That's where request bodies and Pydantic models comes in. By the end of this video, you will know how to define clean typed input contracts for any kind of structured data your AI API needs to accept. First, look at the URL bar at the top. /search, ID equals to 123 and keyword equals to fast API and page equals to 2. That's fine for simple values like ID, a keyword or a page number. But now look at the request body card on the right. A prompt, system instruction, a chat history, a top K value and a stream flag. You can't fit any of that into a URL cleanly. It becomes a mess. Complex structured data belongs in the request body, and the solution is straightforward. You define exactly what that body should look like using a Pydantic model. That's what we cover next. A Pydantic model is a Python class that describes the shape of your data. You inherit from base model and declare each field as typed attribute. Look at the example on the screen. Query request has three fields. Prompt is a required string. Top K is an optional integer that defaults to 5. And stream is an optional boolean that defaults to false. When FastAPI receives a request, it passes the body through this model. Pydantic checks every field against its declared type. If something is missing or wrong, it rejects the request before your function even runs. So, using a Pydantic model in your endpoint is just as simple as defining it. You add it as typed parameter to your function. FastAPI sees that it's Pydantic model and automatically reads the request body and maps it to the model. Look at the /ask endpoint. The request parameter is a type of query request. FastAPI handles everything, passing the JSON body, validating each field, and making the data available through the request object. And because FastAPI knows the model shape, it also adds full input schema to your /docs automatically. So, let's look at a more realistic example. This is a request model for RAG API Karan is building. Prompt is required, every query needs it. System prompt is optional. It lets caller override the default instruction. Top K controls how many document chunks gets retrieved. Score threshold filters out low relevance result below a certain score. And stream tells the API whether to return the answer all at once or token by token. Every field is typed and every optional field has a sensible default. And Pydantic enforces all of it automatically. This is what a clean API contract looks like. But sometimes your request body contains structured data inside structured data. A chat API is a perfect example. Each message in a conversation has two fields: a role, which is either user or assistant, and content, which is the actual text. You define a message model for that and then reference it inside chat request as a list of message objects. Pydantic validates the entire nested structure automatically. If any message in the list has a missing role or content, the whole request is rejected with a clear error. This gives you a deep automatic validation without writing a single validation function. So, to wrap up, when your endpoints need to accept complex structured data, use a pydantic model. Define your field with types and defaults. Pass the model as a function parameter, and FastAPI handles parsing, validation, and documentation automatically. Nested models let you handle complex structures like chat histories cleanly. In the next video, we flip to the other side, response models and status code. You will learn how to control exactly what your API returns and how to communicate the right status to your callers. See you there. Welcome back. In the last video, we covered how to define what goes into your API using pydantic request models. Now we flip to the other side. What comes out? In this video, you will learn how to control the shape of your API responses, filter out data you don't want to expose, and communicate the right status codes to your callers. Let's get into it. Look at the two responses on the screen. On the left, an uncontrolled response. Your function returned a full database object and everything went straight to the caller. A password hash, an authorization token, a database ID, and even debug information with an internal file path. That's a serious security problem. On the right, a controlled response. Only the field you define comes through. ID, name, content, created at, and the score. Clean, safe, and predictable. A response model is what gives you the right side every time. So, defining a response model works exactly the same way as request model. You create a pydantic class with fields you want to expose. Then you pass it to the response model parameter in your route decorator. Look at the example. Document response defines 4 fields: ID, title, summary, and created at. When this endpoints return data, FastAPI checks it against document response. When this endpoints returns data, FastAPI checks it against document response before sending it to the caller. Only those 4 fields go out. Anything else your function returns gets stripped automatically. Here's where response models becomes really powerful. Your internal database object might have many fields: relevant scores, owner tokens, internal flags. You don't want any of that going to the caller. Look at the two models on the screen. DocumentDB has 6 fields, including internal score and owner token. Document response only declares 4. When FastAPI serializes the response, it uses document response as the filter. Internal score and owner token never reaches the caller even if they exist in the object your function returns. You get automatic data protection without writing any filtering logic yourself. Now, status codes are how your API communicates what happened beyond just returning data. Every HTTP response has one. The 200 range means success. 200 is the standard success code. 201 means a new resource was created. The 400 range means problem is on the caller side. 400 is a general bad request. 401 means authentication is missing or wrong. 404 means the resource doesn't exist. 422 is what FastAPI returns automatically when validation fails. The 500 range means something went wrong on your server. In FastAPI, the default status code for any endpoint is 200. You can change it by passing status code to the route decorator. Now, let's put it all together. This endpoint creates a document. It uses response model equals to document response to control exactly what field the caller receives. It uses status code equals to 201. Tell the caller that a new resource was successfully created. Both are set in the decorator. Nothing extra needed. The function itself just returns a dictionary. FastAPI handles validation, filtering, and status code automatically. This is what a clean, complete endpoint looks like: controlled input, controlled output, and correct status code. To wrap up, response model gives you a guaranteed output contract. FastAPI validates and filters your response automatically. Only the fields you declare go out. Status code tells the caller what happened, so use them correctly. 201 for created, 404 for not found, 422 for our validation errors. In the next video, we cover error handling. You will learn how to raise right errors, return useful messages, and handle failure cases cleanly. See you there. Welcome back. So far, we have only written endpoints that work perfectly. But let's be honest, in real life, things go wrong all the time. A document doesn't exist. Someone sends a bad request. An external API times out. The question is, what does your API do in those moments? That's what this video is about. Let's get into it. Here's something that trips up a lot of developers. They focus entirely on making the happy path work and completely ignore what happens when things break. Look at the two examples on the screen. On the left, a bad error, either a 200 with null data or generic internal server error. That tells the caller absolutely nothing. On the right, a good error, status 404, clear message saying exactly what wasn't found, an error code, even a timestamp. The difference matters because whoever is calling your API needs to know what went wrong and why. A bad error response is actually worse than no response. It sends the caller in the wrong direction. FastAPI gives you one clean tool for raising errors: HTTP exception. Import it, raise it, and done. Look at the code. Current's endpoint fetches a document by ID. If it doesn't exist in the database, he raises an HTTP exception with a 404 and the message document not found. That's it. FastAPI catches it automatically and sends a proper JSON error back to the caller. No try catch blocks around everything. No custom middleware, just raise it where the problem happens and FastAPI handles the rest. Now, here's one you get completely for free. Remember the pedantic model we set up. If a caller sends a request that doesn't match your model, wrong type, missing field, whatever, FastAPI automatically returns a 422. And look at how detailed the error response is. It tells the caller exactly which field failed, where it is in the request, and what the problem is. A caller who forgets to send the prompt field gets a response pointing directly at that field. You wrote zero validation code for this. Pydantic and FastAPI did all of it. The detailed field in HTTP exception is just a string by default. That works for simple cases. But what if the frontend needs to show a different message for different error types, or another service needs to handle errors pragmatically? A string isn't enough. Pass a dictionary instead. Look at the example: error code, human readable message, and the specific field that caused the problem. Now the caller doesn't have to pass a string and guess. They check the error code and handle it cleanly. Small change, big difference for anyone consuming your API. Okay, this is the slide you will come back to. Look at the table. 404, resource doesn't exist. 400, input broke a business rule, not just type check. 401, no authentication provided. 403, authenticated but not allowed. 500, something on your server broke. Not the caller's fault. 422, forget it. FastAPI handles it automatically. Two rules that will save you from embarrassing API bugs. Never return a 200 for failure. It confuses every caller. And never return a 500 for something that caller did wrong. That's your API lying about where the problem is. A quick recap: HTTP exception is your main tool. Write status code, clear message, raise it where the problem is. Validation errors are handled automatically. You don't touch them. And when the caller needs to handle errors in the code, use a structured dictionary in detail field. Use the table from slide 6 every time you are not sure which code to pick up. Next up, headers, forms, and files upload. This one is very practical, especially for building ingestion endpoints. Hey, and welcome back. So far, every endpoint we have built receives data either through the URL or through a JSON body. But there are three more ways data comes into your API: headers, forms, and file uploads. And if you are building an ingestion endpoint for current rack system, you're going to need all three. Let's break them down one by one. Look at the three cards on the screen. These are the three request patterns you need beyond path, query, and JSON body. First, headers. On the left, notice the example. It's a GET request with an authorization bearer token and a custom X request ID. That's typically for API authentication and request tracing. Second, form data. In the middle, the example shows a post with application form sending query parameters as a flat key value string. And third, file upload. On the right, that's multi-part boundary in the example is what happens under the hood when you send a PDF. You don't write that manually. FastAPI handles it. Each of these has specific use cases listed at the bottom. Know which tool to reach out for you, and you will handle any request pattern your API needs. Now, headers travel with every HTTP request, but outside the body. The most common use case in AI backends is passing an API key. Look at the code. You import headers from FastAPI and use it as default value for your parameter. FastAPI automatically maps the snake case parameter name, your API key, to HTTP header. Notice the endpoint returns an empty document list if the key is valid and raises a 401 if it's not. Clean one-liner authentication check. We go much deeper on authentication in Module 4, but this is the pattern everything builds on. And now, form data is a different encoding from JSON. Instead of a JSON object in the body, the client sends a flat key value pair. Look at the code. You import from FastAPI and use it instead of pydantic model. Username and password come in as form fields, simple and readable. And one rule you need to remember is, it's on the slide. You cannot mix form field and a JSON body in the same endpoint. FastAPI doesn't allow it. If you need both structured data and file together, that's handled differently, which is exactly what the next slide shows. For file uploads, FastAPI gives you upload file. Import it along with file. use them as a parameter default and you are set. Look at the code. 3 things you will use every time. File.filename gives you the original name of the file. 3 things you will use every time. First, file.filename. It gives you the original name of the file the caller uploaded. Second, file.content type. It tells you what kind of file it is. And third, await file.read. It gives you the raw bytes. Notice the await. Reading file content is input-output bound, so it is async. The return shows all 3 plus the size. Once you have the bytes, you can pass them straight into your ingestion pipeline. And here's the slide that ties everything together for current RAG system. A real ingestion endpoint needs a file and a metadata in the same request. Look at the code. The file comes in as upload file, title is a required form field, and source is optional. FastAPI handles the multi-part encoding automatically. You don't configure anything extra. The function reads the file, returns the file name, title, source, and the size. This is exactly what the /documents/ingest endpoint in Module 6 will look like. You already know how it works before you get there. A quick recap. Headers carry metadata and authentication token. Use headers to read them. And form data handles key value pair from form clients. Use form, file upload, use upload file to get file content and the metadata. And when you need both a file and some metadata in the same request, you can combine file and form fields cleanly. In the next video, we will look at the HTTP methods through real GenAI examples. Get, post, put, patch, delete in realistic AI backend scenario instead of abstract CRUD. See you there. Hey and welcome to Module 3. In Module 2, you build the core building blocks: endpoints, request bodies, response models, error handling. Now we go up a level. In this module, we are going to learn how to structure a growing FastAPI application properly. And it starts with one of the most useful features FastAPI has: dependency injection. Let's get into it. Look at current 3 endpoints on screen: ingestion, query, and config. Every single one starts with the exact same 3 blocks: API key, check database connection, model client initialization. 10 lines of setup code copied 3 times. Now imagine he had 5 more endpoints. That's the same 10 lines in 8 places. Change the authentication logic, update it in 8 places. Miss one, the endpoint is now broken. This is exactly the kind of problem dependency injection was designed to solve. The idea is simple. Instead of writing setup code inside every endpoint, you extract it into a separate function, a dependency. FastAPI calls that function automatically before your endpoints runs. Look at the 2 examples. Without dependency injection, the authorization check lives inside the endpoint function, 8 lines before we even get into the actual logic. With dependency injection, it's 1 line. Depends, verify API key. The setup is completely gone from the endpoint. Your function only does what it is supposed to do. Here's how depends works in practice. You write verify API key as regular Python function. It reads the X API key header, checks it against the expected values, raise a 401 if it's wrong, and returns the key if it's valid. Then in any endpoint that needs authorization, you add API key string equals to you add API key depends verify API key as a parameter. FastAPI sees that, runs verify API key first, and then passes the result in. Look at /documents and /ask at the bottom. Both are now protected with 1 line each. Authorization logic lives in one place. Both endpoints benefit from it automatically. Now, here are the 3 dependencies Karan will actually use throughout his RAG API. First, the authorization check we just saw. Now, reading from setting instead of hard-coded string, which is how you do it in production. Second, the database session. Notice it uses yield instead of return. That means it opens the session, hands it to the endpoint, and then closes it cleanly after the request finishes. We cover yield dependencies in detail in the next video. Third, LLM client. 1 line that returns an initialized OpenAI client using the API key from the settings. Each of these is written once and injected everywhere. So, this slide shows exactly why dependency injection matters for AI backends. Look at the left side. No dependency injection. Every endpoint reinitializes everything from scratch. Validate API key, create a DB session, and the vector store. Every endpoint reinitializes everything from scratch. Validate the API key, create a DB session, init the vector store, init the LLM client, load the config. 5 steps before any business logic runs. Wasteful, error-prone, and a nightmare to test. Now look at the right side. With dependency injection, all 5 of those are shared dependencies created once. Every endpoint just declares what it needs and uses it. The flow diagram at the bottom captures it perfectly. Your config feeds a dependency container. Dependencies are created once, injected into endpoints, and your endpoints stay focused entirely on business logic. That's the architecture you want. So, a quick recap: dependency injection means you write shared logic once and inject it where needed. FastAPI's depends function handles everything. It runs your dependency before the endpoint and passes the result in automatically. In AI backends, this matters a lot because every endpoint needs authorization, database access, and model clients. With dependency injection, all of that lives in one place. Your endpoints stay focused. In the next video, we go deeper. Dependencies with yield. That's how you handle setup and clean up properly for database sessions and external clients. See you there. Hey, welcome back. In the last video, you saw three dependencies: authorization, a database session, and an LLM client. The database session one used yield instead of return. We said we did explain that properly. That's exactly what this video is about. By the end, you will understand why yield exists in dependencies, when to use it, and how FastAPI handles cleanup automatically even when things go wrong. Look at the flow diagram on the screen. Request comes in, dependency runs, return value is passed, endpoint runs, request ends, and then cleanup. With a big red cross, that's the problem. A return-based dependency is done the moment it returns. Once it hands the value to the endpoint, it has no way to run any code after the endpoint finishes. But some resources need exactly that. Database sessions must be closed. HTTP client should be disconnected. File handles needs to be released. If you don't clean up these, you end up with leaked connection and resource exhaustion in production. That's the gap yield fills. Yield splits a dependency into two phases. Look at the code. Everything before the yield is set up. It runs first before your endpoint. The value after yield is what gets injected in your endpoint, and everything after the yield is cleanup. It runs after your endpoint finishes. In this example, setup runs, resource is injected, and the endpoint does its work. And then cleanup runs automatically. The callout at the bottom says it perfectly. Think of it like a try and final block wrapped around your endpoint. That's exactly what FastAPI does internally when it sees a yield dependency. So, here's the most common yield dependency you will write. Get DB. It opens a session local connection, then yield the DB session into the endpoint inside a try block. The finally block closes the connection after the endpoint finishes. The inline comment says it always closes even on error. Look at the endpoint below. The DB parameter just declares depends get DB. The endpoint query starts session by ID and returns the result. It never opens or closes anything. FastAPI wire everything together: open before, inject during, close after. Now, the same pattern works for any external client. Two examples on screen. First, Qdrant vector store client. Qdrant client connects on setup, yields the client to the endpoint, and calls client close in the finally block after the request finishes. Second, an HTTPX async HTTP client. Same structure, but notice the difference. It uses async def and await client a close. This matters because HTTPX async client is async and its close method is coroutine. You must await, and to do that you need an async dependency function. If you use a regular def function here and call a close without await, it won't actually close. Same pattern, but always match async client with async dependency functions. So, this slide shows exactly why finally is the right choice over writing cleanup code after yield. Look at the endpoint. It queries a document by ID. If it's not found, it raises a 404 HTTP exception. Without finally, that exception would bubble up before any cleanup code runs and the session would leak. With finally, it doesn't matter. The comment in the code says it. Directly run even if endpoint raises HTTP exception. The 404 gets raised, FastAPI formats the error response, and before sending it back, db.close executes. No leak sessions. No matter what happens inside your endpoint, the cleanup always runs. So, a quick recap: yield dependency split into two phases: setup before yield, cleanup after. Always use finally for cleanup blocks so it runs even when your endpoint raises an exception. The three most common use cases in AI backends are database sessions, vector store clients, and HTTP clients. All three follow the same pattern: define once, inject anywhere, and your endpoints never have to worry about closing anything. In the next video, we zoom out. As Karan's API grows, a single main.py file isn't enough. We will look at the API router, how to split a growing application into clean, organized modules. See you there. Hey, welcome back. So far, Karan's entire API lives in one file. That's fine when you have three endpoints, but his RAG API now has ingestion endpoints, query endpoints, session management, config, and it's all growing. one file become impossible to navigate very quickly. In this video, we look at API router, fast API's ways to split your application into clean, organized modules. Let's get into it. Look at current's main.py, 9 endpoints already, and the comment at the top says it all, getting out of control. 3 ingestion endpoints, 1 query endpoint, 3 session endpoints, 2 config endpoints, and it's still growing. The warning at the bottom captures the problem perfectly. Too many endpoints in one file, hard to navigate, hard to test, hard to scale. If a teammate wants to work on sessions while Karan works on ingestion, they are both editing the same file. The fix is API router. API router is a mini fast API app for a group of related endpoints. It works exactly the same way as app. Same decorators, same depends, same response models. The only difference is it doesn't run on its own. It gets registered into the main app. Look at the Swagger UI on the right. Notice how endpoints are grouped by tags: users, items, customs, admin. That's exactly what router gives you. Each feature groups has its own section in the docs. Clean, navigable, and easy for any team member to find what they are looking for. So, creating a router takes 3 steps. Import API router from FastAPI, create an instance with a prefix and a tags, then define endpoints on its using @router instead of @app. Everything else stays identical. Look at the code. The router has prefix /documents and tags as documents. That means @router.post/ingest becomes post/documents/ingest, and @router.get document ID becomes get/documents/document ID. You set the prefix once on the router and every route inside it inherits it automatically. The dependencies works exactly the same way. Verify API key and getDB are injected the same way they would be in main.py. And registering routers in main.py is 3 lines. Import each router module, create the app, call include router for each one. That's it. FastAPI registers every endpoint from every router automatically. Look at how clean this main.py is. No pedantic models, no dependency functions, no endpoint logic. Just the app and 3 include router calls. This is what main.py should always look like in real project. An assembly point, not a place where business logic lives. So, this is what Karan's full projects looks like with everything properly organized. Main.py handles app setup and router registration only. Dependencies.py holds all shared dependencies, authorization, DB, LLM, client. Database.py handles the connection setup. The routers folder has one file per feature: documents, sessions, config. The models folder separate request and response, pedantic models into their own files, and .env at the bottom holds environment variables, which we will cover in the next video. Every file has exactly one job. When something breaks, you know which file to open. When you add a feature, you add one router file and one include router line. That's the structure you want. So, a quick recap. API router lets you split your FastAPI application into clean feature modules. Set a prefix on the router and every endpoint inside it inherit it automatically. Register everything in main.py with include router and keep main.py clean. It should only assemble the application, not contain any endpoint logic. In the next video, we tackle settings and environment variable. Right now, Karan has API key and database URL hard-coded or sitting in random places. Pedantic settings gives us a clean, type-safe way to manage all of that. See you there. Hey, welcome back. In the last video, we organized Karan's API into clean router modules. But there is still a problem. API keys, database URLs, and model names are scattered across the codebase, sometimes hard-coded directly into the functions. That's a security risk and a maintenance nightmare. In this video, we fix that properly using pedantic settings. By the end, all of Karan's configuration will live in one place, be type-safe, and be easy to override in the tests. Look at the 3 code blocks on the right. In dependencies.py, the API key is literally typed out as a string in the source code. In router/documents.py, the OpenAI key is hard-coded in the function. In database.py, the full database URL including username and password is hard-coded. Each one has a comment saying hard-coded, which is exactly the problem. On the left, you can see 3 consequences. Secrets get committed to Git. Changing any configuration means tracking it down across multiple files, and there is no clean way to use different values for development, staging, and production environments. All 3 of these go away with pedantic settings. Look at the top diagram first. Your .env file and environment variables feed into pedantic settings, which loads and validates everything automatically and hands your app a typed setting object that's ready to use. Then look at the how it works flow at the bottom. Step 1. You define setting class with type fields. Step 2. Pydantic setting reads value from environment variables automatically. Step 3. If a variable isn't in Step 3. If a variable isn't in the environment, it falls back to your .env file. And step 4. If a required value is missing from both, it raises a clear error before your app even starts. That last step is important. You want to know about the missing config at startup, not halfway through a request. That last step is important. You want to know about the missing config at the startup, not halfway through a request. Now, creating settings look exactly like a Pydantic model because it is one. Inherit from base setting instead of base model and declare each config value as type field. Look at the class API key, database URL, and OpenAI API key have no defaults. They are required. If they are missing, the app won't start. That's intentional. Debug defaults to false, OpenAI model defaults to GPT-4o, Qdren port defaults to 6333. The config inner class at the bottom tells Pydantic settings where to find the .env file and how to read it. Qdren port is declared as int even though environment variables are always strings. Pydantic setting converts it automatically. Now, to use settings safely across the app, wrap the setting constructor in getSettings and decorate it with LRU cache. Look at the top block. GetSetting is a function that returns settings. LRU cache means it only runs once. Every subsequent call returns the same cached instance instead of rereading the .env file. Now, look at the verify API key below it. It takes setting as parameter using depends. It takes settings as a parameter using depends get settings. The hard-coded string is completely gone. The comparison now reads from setting.api underscore key, and at the bottom get underscore LLM underscore client does the same thing. To use settings safely across the app, wrap the setting constructor in the get settings and decorate it with LRU cache. Look at the top block. Get setting is a function that returns settings. LRU cache means it only runs once every subsequent call and returns the same cached instead of rereading the .env file. Now, look at the verify API key below it. Take settings as a parameter using depends get settings. The hard-coded string is completely gone. The comparison now reads from settings API key, and at the bottom get LLM client does the same thing. Setting OpenAI API key instead of hard-coded strings, change the .env file, restart, and every part of app picks up the new values. So, this is where everything comes together for testing. Look at get test settings. It creates a setting instance with test values directly passed in. Test API key, SQL test database, test OpenAI key. Then, the one line below it, app dependency override get settings equals to get test settings. That single line tells FastAPI to use get test settings everywhere get setting is normally injected. For the entire test session, the test below it hits /documents with the test API key and assert a 200. No production values are ever touched. No .env files are modified. No risk of hitting real OpenAI endpoint. This is how you build test suite you can actually trust. So, a quick recap. Never hard code secrets in your source code. Use Pydantic setting to load configuration from the environment variables and .env files. Your setting class gives you typed validated config that fails loudly if anything is missing. Wrap it in LRU cache and expose it via depends so every part of your app gets the same setting instance. And in tests, use dependency override to inject test config without touching .env file or environment variables. In the next video, we cover lifespan, how to load shared resources like ML model and database connection when your app starts and clean them up when it shuts down. See you there. Hey, welcome back. In the last video, we fixed current configuration problem with Pydantic setting. Now there's another issue. Every time an endpoint runs, it's creating a fresh database. Every time an endpoint runs, it's creating a fresh database connection, a fresh vector store client, a fresh LLM client. These are expensive operations. You want to do them once when the app starts and clean them up when it shuts down. That's exactly what lifespan is for. Let's get into it. Look at the two functions on the screen. GetVectorStore creates a brand new Quadrant client on every request, a new TCP connection each time. As the comment says, getLLM client returns a fresh OpenAI HTTP client on every request. Same problem. Both function works, but they are wasteful. The two warning callouts on the left tells you why the first connection overheads on every single request. That setup cost adds up fast under load. Second, no connection pooling. Each request competes independently for new connection. Each request competes independently for a new connection instead of reusing an existing one. The blue callout at the bottom gives you the answer. Create once at startup, share across all requests. That's exactly what lifespan does. Look at the two code blocks on the left. old way. You did write two separate functions, one decorated with app.onEventStartup for initializing and another with app.onEventShutdown for cleanup. They are disconnected, easy to forget one side, and both are deprecated since FastAPI 0.93. On the right, the modern way, one lifespan function with async context manager. Startup code goes before the yield, shutdown code goes after, and you pass it directly to FastAPI with lifespan equals to lifespan. Everything in one place, no deprecated decorators, and the same yield pattern you already know from yield dependencies. The code on the screen shows the skeleton of lifespan function. The three sections are clearly labeled. Startup. Everything here runs once when the app starts, before it accepts any request. In this example, it's just a print message, but this is where you will initialize your clients. Then the yield. This is a single line where the app lives and handles all incoming requests. Shutdown. Everything here runs once the app stops. After the last request is finished, at the bottom, app equals to FastAPI, lifespan equals to lifespan wires it all together. FastAPI manages the full life cycle automatically from that point. So this is current's full lifespan function. The import are on the left, async context manager, FastAPI, Qdent client, async OpenAI, create engine and get settings. The lifespan function is on the right. At startup, settings are loaded first, then the Qdent vector client is created and stored on app.state. Then the async OpenAI LLM client is initialized. Notice, we are using async OpenAI here, not the regular OpenAI client here, because the app is async. Then the database engine is created. The yield app handles request. At shutdown, the vector store client is closed and the database engine is disposed. The LLM client doesn't need explicit cleanup because async OpenAI manages its own connection pool internally. 3 clients, 1 startup, 1 shutdown. So, once resources are on the app.state, you access them through the request object. Look at the left code block. The /ask endpoint injects request directly and pull vector store and the LLM client from request.app.state. This works, but it makes your endpoint function aware of the request object, which is a bit noisy. The right code block shows the cleaner approach. 2 small dependency functions, get vector store and get LLM client. Each take a request and return the resource from app.state. Now the /ask endpoint just declare depends get vector store and depends gets LLM client. The comment at the bottom says it. Clean endpoint, no request object needed, same depends pattern as everything else in the app. Consistent and easy to test. So a quick recap. Heavy resources like database engines, vector store clients and LLM clients should be created once at the startup, not at every request. Use the lifespan context manager. Everything before yield is startup and everything after is shutdown. Store shared resources on the app.state and access them via request object or wrap them in dependency functions for cleaner endpoints. Avoid @app.onEvent because it's deprecated. Now, in the next video, we cover middleware and CORS. If current API is going to be consumed by front-end running on a different CORS needs to be configured correctly. See you there. Hey, welcome back. This is the last video of Module 3. We have covered dependency injection, routers, settings, and lifespan. Now we cover 2 more things that every production API needs, middleware and CORS. Middleware lets you run logic on every request without touching individual endpoints. CORS is what allows a front-end running on different domain to call your API. Both are short to set up and important to get right. Let's go. Middleware is the code that sits between client and your endpoints. Look at the flow diagram at the bottom. Request comes in, hits the middleware first, then goes to the endpoint, comes back through middleware and goes out as response. Your middleware runs on both sides. Now look at the code above. This is a simple logging middleware. It records the start time, calls next request to let the request pass through the endpoint and get a response back. Calculates the duration, logs the method, URL and time and returns the response. That one function now runs on every single request in the application. 0 changes to your endpoint. So here is the production ready version. 3 things happen at the top. A short request ID is generated from UUID and the start time is recorded. And then call next lets the request through. After the endpoint response, the middleware calculates the duration and grabs the status code from the response. The print statement logs all 4 pieces of information together. Request ID, method, path, status code and duration in milliseconds. Then the 2 lines adds the request to the response header as X request ID and return the response. Why does this matter? Because When a caller reports a bug, they can share the X request ID from their browser network tab, and you can search your logs for the exact request ID and see everything what happened. Now, CORS means cross-origin resource sharing. It is a browser security feature. By default, browser blocks JavaScript from making requests to different origin than the page it's running on. And origin is the combination of protocol, domain, and port. Look at the example. A front end on localhost 3000 and an API on localhost 8000 are different origins, different ports. A front end on app.current.com and api.current.com are different origin, different subdomains. When Current's front end tries to call his API through CORS configured, the browser blocks it completely. The API must respond with the right header to tell the browser it's allowed. So, this is a browser restriction only. Postman, curl, and server-to-server calls are not affected. Now, FastAPI ships with CORS middleware built in. You add it with app.add_middleware and configure your 4 key parameters. Allow origins is a list of front-end origins that are allowed to call your API. Allow credentials, allow cookies and authentication headers to be sent. Allow methods, control which HTTP method are permitted. Allow header, controls which request header the front-end can send. The example shows a typical development setup. The React frontend on localhost 3000 is allowed. Credentials are enabled and all methods and headers are permitted. But for production, you want to be more specific, which we cover in the next slide. In development, broad CORS settings are fine. Wildcard origins, all methods, all headers. It's your local machine and you want things to work quickly. In production, you lock it down. List only specific front-end origins that should be allowed. Enumerate only methods your API actually uses. List only headers your front-end actually sends. One critical rule, you cannot combine allow origin star with allow credentials equals to true. Browser will reject this combination because allowing all origins with credential is a security risk. Always use specific origins when credentials are needed. And the bottom of the slide shows the clean way to handle this. Store your allowed origins as a comma separated string in setting. Split it at runtime and pass it to CORS middleware. Now your CORS config changes with your environment without touching the code. So that wraps up Module 3. A quick recap. Middleware runs on every request and response. Use it for logging, request tracing, and security headers. CORS tells browser which frontend are allowed to call your API. List specific origins in production and never combine wildcard origins with credentials. Current's API now has a clean router, type setting, shared resources loaded at the startup, and middleware running globally. That's real production grade structure. Up next is the Module 3 quiz. It covers dependency injection, API router, settings, lifespan, and middleware. Good luck and I'll see you in the Module 4. Hey, welcome to Module 4. So far, Karan's API is well structured. Clean routers, type settings, shared resources at startup. But there's one big problem. Anyone who knows the URL can hit his endpoints. Every unauthenticated call to his RAG API triggers an LLM call, which costs money. In this module, we fix that. We start with the simplest and most practical auth pattern for AI backends, API key authentication. Let's get into it. Think about what an OpenAI API means in practice. Every call to post/ask triggers an embedding call and an LLM call. Those aren't free. If Karan deploys this without auth and someone discovers the URL, they can run thousands of queries against his OpenAI account and he pays the bill. That's before we even talk about data security. Anyone can read session history, ingest garbage into his vector store, or delete documents. This isn't hypothetical. Exposed AI AP gets scraped and abused constantly. The simplest fix is API key authentication, a secret key that every caller must include with their request. API key authentication is the simplest auth pattern there is. The caller includes a secret key in a request header alongside every request. The server checks that key before doing anything else. If it's missing or wrong, the server returns a 401 and the request goes no further. If it's correct, the request proceeds normally. Look at the example headers. The key travels in X-API-key, a custom header. The server never stores sessions, never issues tokens, never manages login flows. It just checks one header value. This makes it stateless, lightweight, and perfect for server-to-server communication and internal AI tools where you control who has the key. You've actually seen this dependency before. We built it in Module 3. Let's look at it properly now. Verify_API_key takes the X-API- key header as optional open bracket, str close bracket. So a missing header doesn't trigger a 422 before we can return a proper 401. Then two checks. First, Is the key missing entirely? If so, return a 401 with a message that tells the caller exactly what to do. Second, is the key present but wrong? Another 401 different message. Why separate messages? Because when a caller gets a 401, they need to know whether they forgot to send the header at all or sent the wrong value. Specific error messages save debugging time. The key is compared against settings.api_key. No hard-coded strings anywhere. FastAPI gives you 3 places to apply the verify_API_key dependency. First, individual endpoints. Add it as a parameter to one specific function. Good when only some endpoints need protection. Second, the entire router. Pass it in the dependencies list when creating the router. Every route in that router is now protected without touching individual functions. Third, the entire application. Pass it when creating the FastAPI app. Every endpoint in every router is now protected. For Karan's RAG-API, router level protection is usually the right call. His documents, ask and sessions routers all need auth. His health check endpoint probably doesn't. Router level gives him that granularity cleanly. API key auth is powerful for its simplicity, but it has real limits. It fits well when you're building internal tools, server-to-server integrations, or early-stage AI products where you control who has the key. It's a yes/no gate. This caller is allowed or they're not. Where it breaks down is when you need user-level identity. If Karan's RAG API needs to know which specific user is asking, show them only their own sessions or give different users different permissions. A single API key shared across callers can't do that. For those scenarios, you need OAuth 2 and JWT, which is exactly what we cover in the next video. For many AI backends though, especially internal ones, API key auth is exactly enough. Quick recap. API key authentication is one header and one check. Build it as a fast API dependency so it's reusable across every router and endpoint that needs it. Apply it at the right level. Individual endpoint for selective protection, router level for feature group protection, app level for full lockdown. And remember its limits. It protects your API from unauthorized callers but doesn't give you user-level identity or permissions. In the next video, we cover OAuth 2 and JWT, when you need to know not just that a caller is allowed, but exactly who they are and what they can do. Hey, welcome back. In the last video, we added API key auth to Karan's API. That works well when you control who has the key. But what happens when his RAG API has real users, each with their own sessions, their own documents, their own query history? A single shared API key can't tell you which user is making the request. That's where JWT come in. In this video, we cover what a JWT is, how the auth flow works, and how fast API reads a token to identify the user. Let's get into it. Look at the top panel on screen. API key auth answers one question. Is this caller allowed? That's it. But look at what multi-user AI backends actually need. The 3 check marks on the right. Which user is making this request? Show them only their own data. Give different users different access levels. A shared key can't do any of that. Everyone looks the same. The 3 cards at the bottom make this concrete. ARAG API with 100 users where each user sees only their own documents. A team product where admins can delete but members can only query. A multi-tenant system where company A's data never leaks to company B. JWT solve all 3 by carrying the user's identity inside the token itself. JWT stands for JSON Web Token. A JWT is a string with 3 parts separated by dots. Look at the diagram. The first part, the header, tells you the algorithm used to sign the token. The second part, the payload, is the useful bit. It carries user data, ID, email, role, and expiry. The third part, the signature, is a cryptographic hash generated with a secret key. Here's why this matters. Anyone can read the payload, but nobody can modify it without invalidating the signature. Look at the flow diagram at the bottom. The client sends the JWT to your API. Your API verifies the signature. Valid, the payload is trusted. Invalid, the token is rejected. If someone tampered with the payload, the signature won't match. Here's the full flow. Step 1. The user logs in. They send their credentials to an auth provider. This could be Auth 0, Supabase, Firebase Auth, or any other service. Karan's Fast API never sees the password. Step 2. The auth provider verifies the credentials and issues a JWT containing the user's ID, email, role, and an expiry time. Step 3. The front end receives this token and stores it. Every subsequent request to Karan's API includes the token in the authorization header as a bearer token. Look at the example header. Step 4. Karan's Fast API receives the token, verifies the signature, and reads the user's identity from the payload. The request is processed based on who the user is. Karan's API is a consumer of the auth system, not the owner of it. That separation is the right design. Look at the code on the right. OAuth 2. Password bearer handles extracting the bearer token from the authorization header automatically. You don't pass the header yourself. The function is get_current_user. It takes the token string and decodes it using jwt.decode with the jwt_secret from settings and hs256 as the algorithm. It then reads user_id from the subclaim. Sub is the standard JWT field for subject, which is the user identifier. If the token is missing, expired or tampered with, JWT error is raised and the function returns a 401. If everything checks out, it returns a dictionary with the user's ID and email. Any endpoint that declares depends open parenthesis get_current_user close parenthesis now has the user's identity available. Look at list_sessions. It doesn't return all sessions. It filters by current_user open bracket quote user_id quote close bracket. User A only ever sees their own sessions. Look at the ask endpoint. The vector store search uses the user ID to build the collection name. User_open brace current_user open bracket single quote user_id single quote close bracket close brace. User 123 never gets results from user 456's documents. That's multi-tenant RAG in its simplest form. One API, multiple users, complete data isolation. And because get_current_user is a dependency, every endpoint that needs user identity just declares it. No repeated token parsing, no security logic scattered across functions. Quick recap. A JWT is a signed token that carries user identity. Your FastAPI verifies the signature and reads the user's ID, email, and role from the payload. The auth flow is clean. An auth provider handles login and token issuance. Your API just verifies what it receives. Build get_current_user as a dependency and inject it into any endpoint that needs to know who's calling. Use the user ID to filter database queries and vector store searches. That's the foundation of per user RAG. In the next video, we cover rate limiting and abuse protection. Even with auth in place, a single authenticated user can still overload your API or run up your LLM costs. Rate limiting is how you prevent that. See you there. Hey, welcome back. We've added API key auth and JWT-based user identity to Karan's API. But there's still a gap. A single authenticated user can hammer the /ask endpoint 1,000 times in a minute. Each call triggers an LLM request. That's real money and a degraded experience for every other user. Rate limiting is how you put a ceiling on that. In this video, we cover what rate limiting is, how to implement it in FastAPI using slow API, and how to handle the case when a user hits their limit. Think about what one call to post/ask actually costs. An embedding call to convert the query into a vector, an LLM inference call to generate the answer, a vector database query in between. None of these are free. Now multiply that by a buggy front end that retries in a loop, or a heavy user running automated queries, or someone who just discovered your URL. Without rate limiting, your OpenAI spend becomes completely unpredictable. You have no ceiling, no early warning, no way to protect your budget. Rate limiting fixes this by putting a hard cap on how many requests any single caller can make in a given time window. It's not just a security feature, it's cost control, predictable usage, predictable spend, and fair access for every user on your API. Rate limiting is straightforward conceptually. You pick a limit, say 10 requests per minute per user, and track how many requests each user has made in the current window. Once they hit the limit, any further requests in that window get a 429 response. The window resets and they can start again. Look at the example. User A makes 9 requests, all fine. Their 10th in the same minute gets a 429. User B is completely unaffected. Their limit is tracked independently. Two decisions to make: what to limit by and what the window is. For Karan's API, limiting by user ID is the right call since he has JWT auth. Each authenticated user gets their own independent quota. Slow API is the go-to rate limiting library for FastAPI. Install it with pip, create a limiter instance, attach it to app.state, and register the built-in exception handler for when limits are exceeded. Then decorate any endpoint with that limiter.limit and pass a human-readable limit string. 10 per minute means 10 requests per minute. 100 per hour means 100 per hour. The library tracks the count, and when a caller exceeds their limit, the exception handler automatically returns a proper 429 response. The example uses IP address as the key, meaning each IP gets its own independent limit. For most quick setups, this works fine, but for Karan's API with real user identity from JWTs, we can do better. IP-based limiting has a problem. Multiple users behind the same corporate proxy share one IP address. They'd all hit each other's limits. The fix is to limit by user ID instead. Look at get underscore user underscore ID underscore from underscore token. It tries to extract the user ID from request.state, which is where your auth middleware puts it, and falls back to IP if there's no authenticated user. You pass this function as key underscore func to the limiter. Now each authenticated user has their own independent quota. User A making 10 requests doesn't affect user B at all, and unauthenticated callers still get limited by IP. One key function, two behaviors, right tool for each case. When a user hits their limit, they get a 429. The default slow API response is a simple error string. That works, but it's not very helpful. Look at the custom handler. The response now includes a clear error message, tells the user what their limit is, and adds a retry after header. That header is important. Well-behaved HTTP clients and frontends read it and automatically wait before retrying instead of immediately hammering the API again. A good 429 response turns a frustrated user into a patient one. Register your custom handler with app.add_exception_handler, and every rate limit hit across your entire application gets the same clean response. Quick recap. Rate limiting is essential for AI backends because every request has a real cost. Slow API gives you decorator-based limits in a few lines of code. Limit by user ID when you have JWT auth, so each user gets their own independent quota. And when a limit is hit, return a clear 429 with a retry after header, so callers know when to try again. In the next video, we cover input validation and prompt injection defense. Even with auth and rate limiting in place, a malicious user can still try to manipulate your LLM by crafting clever prompts. That's the next layer of protection we need to add. See you there. Hey, welcome back. So far, we've built a well-structured, authenticated, rate-limited API. But how do you know it actually works? And how do you know it keeps working every time you make a change? That's what testing is for. In this video, we cover automated testing with PyTest and FastAPI's test client. By the end, you'll have a working test suite for Karan's RAG API. Let's get into it. A bug in a regular web API is annoying. A bug in a RAG endpoint is expensive. Wrong retrieval logic means users get bad answers and lose trust in the product. A broken auth check means a security incident. A silent change to a response model means the front end breaks in production and nobody knows why until a user complains. Automated tests catch all of this before deployment. They give you confidence to refactor and add features without worrying about breaking what already works. And when something does break, a failing test tells you exactly where, instead of you piecing it together from production logs at 2 a.m. The setup is minimal. Install PyTest and HTTPX. Test client uses HTTPX under the hood. FastAPI's test client is built in, no extra install needed. The key file is conftest.py. This is PyTest shared configuration file. Anything you define here is automatically available to every test file in your project. Look at the client fixture. It wraps your FastAPI app in a test client and yields it. The white block is important. It triggers your lifespan function, so startup code runs before test and cleanup runs after. Every test that declares client as a parameter gets a fresh, fully initialized test client. Writing a test is straightforward. Use the client fixture to make a request just like you would with any HTTP client. Call client.get with the path and any headers you need. Then assert. Always check the status code first. If that's wrong, the body doesn't matter. Then check the response body. Look at the two tests on screen. The first hits /documents with an API key and asserts a 200 and a list response. The second hits /health and asserts an exact JSON response. These are simple, but they're real value. If someone accidentally breaks the document's endpoint or changes the health check format, these tests fail immediately. For post endpoints, pass your request body as JSON equals and headers as headers equals. Look at the ask test. It sends a valid RAG query request as a JSON dictionary and asserts a 200 response with an answer field that's a string. That's enough to know the endpoint is wired correctly. The second test is more interesting. It tests file upload. PyTest's TMP path fixture gives you a temporary directory to create test files. The test creates a small text file, opens it, and sends it as a multi-part upload alongside a form field. These two patterns, JSON equals and files equals, cover the majority of what you'll test in an AI backend. Happy path tests tell you things work when they should. Error case tests tell you things fail correctly when they should. These are equally important. Look at the 4 tests on screen. Missing API key should return 401, not 200, not 500. Wrong API key should also return 401. A request missing the required prompt field should return 422. FastAPI's automatic validation error. And a request for a document that doesn't exist should return 404. If any of these tests fail, it means your error handling is broken. A missing API key returning 200 is a security bug. A missing field returning 500 means your validation isn't working. Error case tests are how you prove your API fails safely. Quick recap. PyTest and FastAPI's test client give you everything you need to test your API without running a server. Set up your client fixture in confTest.py so it's available across all test files. Write tests for happy paths, valid requests returning the right status and shape. Write tests for error cases, missing auth, bad input, not found. And name your tests clearly so when one fails, you know exactly what broke without reading the code. In the next video, we go deeper. Dependency overrides for testing auth and database logic cleanly, and async tests for endpoints that use async dependencies. See you there. Hey, welcome back. In the last video, we wrote tests for Karan's endpoints using PyTest and test client. But there's a problem with those tests. Every time they run, they hit the real database, the real vector store, and potentially the real OpenAI API. That's slow, expensive, and unpredictable. If the database is down, every test fails. If OpenAI is slow, your test suite takes minutes. In this video, we fix that with dependency overrides, FastAPI's built-in way to swap real dependencies with lightweight test versions. Let's get into it. The red panel on the left shows what happens with real dependencies and tests. Slow, expensive, fragile, and they pollute your test data. The flow below it shows why. Your test hits the database, then the LLM API, then an external service. Any one of those failing breaks every test. The green panel on the right shows what overrides give you instead. Fast, isolated, repeatable, reliable. The flow simplifies to test hits a mock, gets a stable result. That's it. Good tests should give you the same result whether you run them on your laptop in CI or at 3 a.m. when every external service is down. Dependency underscore overrides is a dictionary that lives on your FastAPI app object. Look at the code on the right. The key is the original dependency function. The value is your test replacement. Get underscore DB normally opens a real PostgreSQL session via session local. Get underscore test underscore DB opens a test session local instead. One line at the bottom, app.dependency underscore overrides open bracket get underscore DB close bracket equals get underscore test underscore DB. From that point on, every endpoint that declared depends open parenthesis get underscore DB close parenthesis now gets get underscore test underscore DB automatically. No changes to your endpoint code, no conditional logic. FastAPI handles the swap completely. The override stays active for the entire test session until you clear it. Or dependencies block every test that hits a protected endpoint. Without overriding, every test that needs a real JWT either depends on your auth provider being up or requires you to generate valid tokens in your test setup. Neither is clean. Look at the code on the right. Get underscore test underscore user returns a fixed dictionary with a known user. ID, email, and role. No JWT parsing, no network call. The authenticated underscore client fixture sets app.dependency underscore overrides open bracket get underscore current underscore user close bracket equals get underscore test underscore user before yielding the client. Then calls app.dependency underscore overrides dot clear parents afterward. Now look at unauthenticated underscore client at the bottom. No override is set. It uses a plain test client. Keep this fixture too because you still need to verify that auth actually rejects unauthenticated requests. Two fixtures, two separate concerns. Look at the code panels on screen. It has three things. First, get underscore test underscore DB, which creates a test session local bound to a SQLite in memory engine using SQLite ://:memory:. Fast, disposable, no external connection. Second, get underscore mock underscore LLM, which creates a magic mock and sets a fixed return value on mock.chat.completions.create. The mock returns the string, this is a test answer, instantly with no OpenAI call and no cost. Third, get underscore mock underscore vector underscore store in the right panel, which returns a magic mock with search.return underscore value equals an empty list. The test underscore client fixture at the bottom of the right panel wires all three overrides together. Get underscore DB, get underscore LLM underscore client, and get underscore vector underscore store are all swapped. It yields the client and then calls app.dependency underscore overrides dot clear parents. Any test using this fixture runs completely isolated from external infrastructure. Test client from the previous video is synchronous. It blocks until the response comes back. That works for most tests, but if you're testing async streaming endpoints or async background tasks, you need an async test client. Look at the two blocks on the right. First, the pytest.iniconfig. Set asyncio underscore mode equals auto. This tells pytest-asyncio to automatically handle async test functions. Then look at the Python test. It imports async client from HTTPX instead of test client. The test function is async def and decorated with @pytest.mark.asyncio. Async client is used as an async with context manager with base underscore URL equals quote http://test quote. Everything else, sending the request and asserting the response, works exactly the same as the synchronous version. Use async tests specifically when you need to test async behavior. For regular endpoint tests, test client is simpler and sufficient. Quick recap. Dependency underscore overrides lets you swap real dependencies with lightweight test versions. No changes to your endpoint code. Override auth to inject a fixed test user. Override your DB with SELite in memory and mock your LLM and vector store clients. Always clear overrides after each fixture. Use async client and PyTest asyncio only when testing async specific behavior. For everything else, test client is simpler. Next up, Postman for manual verification. See you there. Hey, welcome back. We've spent the last two videos building a solid automated test suite with PyTest that covers regressions and catches bugs before deployment. But sometimes you just want to quickly fire a real request at your running API and see what comes back with your own eyes. That's where Postman comes in. In this video, we use it as a manual verification tool, not a replacement for automated tests. A spot check on top of them. Let's set it up. Look at the flow on screen. Code change, PyTest runs, deploy, Postman spot check. That's the full development workflow. Automated tests run on every code change and in CI. They catch regressions without any human involvement. But after you deploy to a new environment, whether that's staging or production, you want a human to fire a real request and confirm things are working as expected. That's exactly where Postman sits. The callout at the bottom says it clearly. Postman is used by a human for a quick sanity check on a running API. This is exactly what Postman does mechanically. You enter your request in Postman targeting localhost :8000/ask. It travels to the FastAPI server, the server receives it, processes it, builds the response. That response comes back to Postman and you see it on screen. 200 OK with Karan's answer in the body. The whole thing takes 2 seconds. No code, no fixtures, no mocks. Just a real request and a real response. That's the value. Use it as your spot check, not your safety net. PyTest is the safety net. The use cases of Postman. Verifying an endpoint works after deploying to a new environment. Exploring a response structure you haven't tested yet. Sharing a working request example with a teammate or front-end developer. And quick debugging without writing a formal test first. All four have one thing in common. They need a human in the loop looking at the actual response. That's what Postman gives you. Your automated test suite is the safety net. Postman is the spot check. Let's switch to Postman to see it live. That's Postman setup and working with Karan's API. You now have automated tests for regressions and a fast manual check for deployments and exploration. That's a complete testing workflow. Up next is the Module 4 quiz, covering API key auth, JWT, rate limiting PyTest, dependency overrides, and Postman. Good luck and we'll see you in Module 5. Hey, welcome to Module 5. Karan's RAG API is working well for single queries. But there's a problem. Every request is completely independent. Ask a follow-up question and the API has no idea what you asked before. Real users expect a conversation, context that carries across multiple turns. In this module, we tackle state, persistence, and long-running work. We start with the foundational question: what should the API layer own and what belongs in storage? Let's get into it. Look at the conversation on screen. The user asks, what did the guest say about AI safety? The API answers correctly. Then the user sends a follow-up. Can you expand on that? Look at what happens. The API has no idea what that refers to. No memory of the previous question. No memory of the previous answer. It receives this as a completely new independent request. That's the stateless problem. And it's not just about follow-up questions. It's about user sessions, conversation history, personalization, and agent memory. The callout at the bottom says it. Real conversational AI needs context across turns. Solving this cleanly requires understanding what the API layer should own versus what belongs in storage. As shown in the diagram, 3 separate requests, 3 separate users, 3 separate API server instances, 3 independent responses. Request 1, user A does a get on/users, gets a 200 back. Request 2, user B does a post to /orders, gets a 201. Request 3, user C deletes an item, gets a 204. Each request hits the server, gets processed, gets a response, and the server immediately forgets everything. No shared context, no memory between them. The benefits of it are as follows. Simple to scale because any server instance can handle any request. Easy to test because there's no shared state to set up or clean up. Predictable because the same input always produces the same output. HTTP itself is stateless by design. These are real advantages, but the limitation is clear. If you need to remember something across requests, the server can't help you. That state has to live somewhere external. Now look at this diagram. Same three requests coming, but now there's a single API layer in the middle coordinating all of them, and a shared state layer on the right. Look at what's stored there. Chat history, previous turns in a conversation, user sessions, who is logged in and what they've done, ingested documents, what a user has uploaded to their knowledge base, agent memory, what steps an agent has completed in a workflow. The API layer coordinates requests and reads and writes to that shared state. That's the keyword, coordinates. It doesn't store anything itself. When Karen/ask endpoint handles a query, it reads the conversation history from the database, adds it to the prompt context, calls the LLM, then writes the new exchange back. FastAPI is the middleman. The state lives in storage, not in the server. Here's the clean boundary. FastAPI's job is to receive requests, validate them, authenticate the caller, orchestrate the retrieval and generation pipeline, and return a formatted response. That's it. The storage layer's job is to remember everything: chat history, user sessions, ingested documents, agent state. When Karan/ask endpoint handles a query, it reads the conversation history from the database, adds it to the prompt context, calls the LLM, then writes the new exchange back to the database. FastAPI is the coordinator in the middle. It never holds state itself. This separation is what makes the system scalable. You can run 10 FastAPI instances and they all read and write to the same shared storage. 5 types of state, what each one is and where it lives. Chat history is structured, ordered, and queried by user and session. That's relational data. PostgreSQL is the write home. Document knowledge base is ingested and chunked documents that need similarity search. That goes in a vector store like Quadrant. Agent state, steps completed, and tools called needs to survive between turns but is often short-lived. Database or Redis depending on how long it needs to persist. User preferences, per user settings, and model config are relational. Relational database again. Cached responses for frequent queries with reusable answers go in Redis for speed. Each type of state has a natural home. Match the state to the right storage system and you avoid a lot of performance and scaling problems later. Quick recap. Stateless means each request is independent. Simple to scale but no memory. Stateful behavior means the system remembers across requests and that memory lives in storage, not in FastAPI itself. FastAPI's job is to coordinate. Read from storage, process, write back. Keep that boundary clean and your system stays scalable and testable. In the next video, we get practical. Building the chat history layer with a relational database. Karan's API will finally be able to have a real conversation. See you there. Hey, welcome back. In the last video, we established that FastAPI coordinates state but doesn't store it. Now we build the storage layer. In this video, we cover the relational database schema for a chat product, what tables you need, how they relate, and how to read and write chat data through FastAPI using SQL Alchemy. By the end, Karan's API will be able to store and retrieve full conversation history. Let's get into it. Think about what a real chat product needs to remember. First, users, who is making requests. Second, sessions, a named conversation that groups related messages together. Third, messages, the individual turns, the user's prompt and the assistant's response. Fourth, metadata, the operational detail attached to each message. Which model was used, how many tokens were consumed, how long the response took. These 4 things form a natural hierarchy. One user can have many sessions. One session can have many messages. Each message carries its own metadata. Get this structure right and you can build everything from basic chat history to usage analytics and cost tracking. Here's the schema. 4 tables. Users has the basics, ID, email, and when the account was created. Sessions belongs to a user via user_ID and has a title and timestamps. Messages belongs to a session via session_ID and has a role field, either user or assistant, and the content. Message metadata is a separate table linked to each message, storing the operational details, which model generated the response, how many tokens were used, how long it took, and the cost. Keeping metadata in a separate table is a deliberate choice. It keeps the messages table clean and fast to query, and you can analyze costs and performance independently without touching the core chat data. Here are the SQL Alchemy models. Each class maps to a database table. User has a sessions relationship, one user to many sessions. Session has a user relationship back to user, and a messages relationship forward to message. Message has a session relationship back to session. The foreign key columns, user underscore ID in session and session underscore ID in message, are what enforce the hierarchy in the database. The relationship calls tell SQL Alchemy how to navigate between models in Python. Notice declarative base from the latest SQL Alchemy. This is the modern way to define your base class, replacing the older declarative underscore base function. Here are the two most important operations. Creating a session. The endpoint reads the user ID from the JWT, creates a new session object with that user ID, adds it to the database session, commits and refreshes to get the generated ID back. That last step, db.refresh, is important. Without it, session.id won't be populated yet because the database generates it. The second endpoint retrieves all messages for a session, ordered by creation time. Note the order underscore by. Always return messages in chronological order, or the conversation history won't make sense when you pass it to the LLM. Metadata is what turns a chat product into an observable system. Every LLM response comes with usage data, token counts, model name, and you can calculate cost from those. Store all of it in the message underscore metadata table. Look at the usage query at the bottom. With this data, Karan can answer, how many tokens has this user consumed this month? What's their total cost? Which sessions are the most expensive? This is the foundation for usage-based pricing, budget alerts, and capacity planning. It costs almost nothing to store and it's extremely valuable operationally. Always capture it. Quick recap. A chat product needs 4 tables: users, sessions, messages, and message metadata. Keep metadata separate so your core chat queries stay fast and you can analyze usage independently. Always order messages by creation time and capture token counts and latency with every single LLM response. It costs nothing to store and pays off when you need to understand your system's behavior and cost. In the next video, we switch from relational to vector storage. How documents are chunked, embedded, and indexed for retrieval in Karan's RAG system. See you there. Hey, welcome back. We've covered relational databases for storing chat history and user data, but Karan's RAG system needs a different kind of storage for documents. When a user asks a question, the system needs to find the most relevant chunks of text from thousands of documents, not by keyword matching, but by meaning. That's what vector databases are built for. In this video, we cover how vector storage works, how documents get indexed, and how retrieval happens. This is the foundation for the RAG project in Module 6. Let's get into it. A SQL-like query finds documents that contain specific words. If a user asks, how does attention work in language models? And your documents talk about transformers and self-attention but never use the word attention mechanism in that exact form, the keyword search misses them entirely. RAG needs semantic search, the ability to find content that means the same thing even when different words are used. This is what embeddings enable. Instead of storing text, you store a mathematical representation of the text's meaning. Then you find documents whose meaning is closest to the query's meaning. Vector databases are built specifically for this kind of search. An embedding is a list of numbers, typically 768 to 1536 of them, that represents the meaning of a piece of text. The key property is this: text with similar meaning gets similar numbers. Look at the two examples. FastAPI handles async requests efficiently and async support in FastAPI improves concurrency are different sentences but mean similar things. Their embeddings are close to each other in the vector space. A vector database stores these embeddings alongside the original text. When you search, it converts your query to an embedding and finds the stored embeddings that are closest to it. That's semantic search. The algorithm for finding close vectors quickly is called approximate nearest neighbor search, and it's what makes vector databases fast even at millions of documents. Before any document can be retrieved, it goes through 3 steps. Step 1. Chunking. The full document is split into smaller pieces, typically 200 to 500 words each. Why? Because embedding a 50-page document as one vector loses too much detail. Smaller chunks give more precise retrieval. Step 2. Embedding. Each chunk is sent to an embedding model. We are using OpenAI's text embedding 3 small here and convert it to a vector. Step 3. Indexing. Each chunk and its embedding are stored in Quadrant as a point. A point has an ID, a vector, and a payload. The payload is where you keep the original text and any metadata you want to return with search results. Run these 3 steps for every document a user ingests and your vector store is ready for retrieval. Retrieval is the mirror of ingestion. Step 1. Embed the user's query using the same embedding model used during ingestion. This is critical. You must use the same model both times or the vectors won't be comparable. Step 2. Search the vector store for the closest vectors to the query embedding. The limit parameter controls how many results come back. Top underscore k is typically 3 to 5 for RAG. Step 3. Extract the text from the payload of each result and return it. These chunks are then passed to the LLM as context alongside the user's question. The LLM reads the retrieved chunks and generates an answer grounded in current documents. That's the complete RAG loop. Quadrant is the vector store we use in this course. It's open source, can be self-hosted with Docker, and has a managed cloud option. The three concepts to know. A collection is a named group of vectors. Think of it like a table in SQL. Each collection has a fixed vector size that must match the output of your embedding model. For OpenAI's text embedding 3 small, that's 1536 dimensions. A point is one stored item. It has an ID, a vector, and a payload. The payload is a JSON object where you store the original text, document metadata, user ID, or anything else you want returned with search results. Distance.cosan is the similarity metric. It measures the angle between vectors, which is the standard approach for text embeddings. Get these three right and Quadrant works exactly as expected. Quick recap. Vector databases store numerical representations of meaning and find similar content through approximate nearest neighbor search. The ingestion pipeline is chunk, embed, index. Run this for every document a user uploads. The retrieval pipeline is embed the query, search the vector store, return the top chunks, pass them to the LLM. One rule you must always follow. Use the same embedding model for both ingestion and retrieval. If they don't match, your searches will return garbage. In the next video, we cover conversation memory patterns, how to differentiate between short-term request context, persistent chat history, and retrieval memory, and when to use each one. See you there. Hey, welcome back. In the last two videos we covered were state lives, relational databases for chat history, vector stores for documents. Now we go one level up and talk about memory patterns. In a GenAI system, memory isn't one thing. It's three distinct things that work together: short-term context, persistent chat history, and retrieval memory. Understanding the difference is what separates a basic chatbot from a real conversational AI product. Let's break them down. There are three types of memory in a GenAI system, and they're easy to mix up. Short-term context is everything inside the LLM's prompt window for one request. The system prompt, the recent conversation turns, and the retrieved chunks. It exists only for the duration of that single request. Persistent history is the conversation stored in your database, turns from previous requests that you selectively load and inject into the prompt. Retrieval memory is your document knowledge base in the vector store. It doesn't store conversation, it stores knowledge that any query can retrieve from. Each type has a different job, a different storage home, and a different scope. Get the boundaries right and your system becomes much easier to reason about. Short-term context is everything you assemble into the prompt for one request. Look at the function. It starts with a system prompt that sets the assistant's behavior. Then it adds recent conversation turns from the persistent history. Then retrieve chunks from the vector store as additional system context. Then the current user query. This assembled list of messages is what gets sent to the LLM. Once the response comes back, this context is gone. It was only ever in memory. The LLM never sees previous requests directly. Everything it knows about the conversation comes from what you explicitly include in this prompt assembly step. That's why the next two memory types exist, to give you something to include. Persistent history is the conversation stored in your database, but you don't load the entire history into every prompt. That would quickly exceed the LLM's context window limit. Instead, you load only the last and turns. Look at the function. It queries the most recent messages in reverse order, takes the last 10 turns, which is 20 messages since each turn has a user message and an assistant response, then reverses them back to chronological order before returning. As the conversation grows, older turns naturally drop off the prompt. The database keeps the full history forever. The LLM only ever sees the recent window. This is the right balance between context and token efficiency. Retrieval memory is completely separate from conversation history. It's the document knowledge base in your vector store. When a query comes in, you search the vector store for the most relevant chunks, not based on what was said before, but based on the semantic meaning of the current question. Look at the function. It searches the user's personal collection, scoped by user ID, and returns the top matching chunks. Retrieval memory is stateless. The same query always returns the same results regardless of conversation history. It doesn't know what was discussed before. It only knows what documents exist. This separation is powerful. You can have a user with thousands of ingested documents and retrieval stays fast because vector search scales well. When a user hits their limit, they get a 429. The default slow API response is a simple error string. That works, but it's not very helpful. Look at the custom handler. The response now includes a clear error message, tells the user what the limit is, and adds a retry after header. That header is important. well-behaved HTTP clients, and front ends read it and automatically wait before retrying instead of immediately hammering the API again. A good 429 response turns a frustrated user into a patient one. Register your custom handler with app.add_exception_handler, and every rate limit hit across your entire application gets the same clean response. Quick recap. Short-term context is assembled per request and lives only in the prompt. Persistent history lives in the database. Load only recent turns. Retrieval memory lives in the vector store. Stateless and fast. Always save the new exchange to the database after responding. Next up, background tasks. What to do when an operation takes too long to complete within a single request. See you there. Hey, welcome back. So far, every endpoint we've built returns a response only after all the work is done. That's fine for a quick database query or a short LLM call. But what about document ingestion? Chunking a 50-page PDF, generating embeddings for every chunk, and indexing everything into QDRANT can take 10 to 30 seconds. Holding the HTTP connection open for that long is a bad experience. In this video, we cover background tasks, how to return a response immediately and continue the work after. Think about what happens when a user uploads a 100-page PDF to Karan's RAG API. The endpoint has to read the file, split it into chunks, call the embedding API for each chunk, and index everything into QDRANT. That's easily 20 to 30 seconds. During all of that, the HTTP connection is open and the caller is sitting there waiting. Most proxies and API gateways have a 30 to 60-second timeout. If the file is large enough, the connection drops before the work is done and the caller gets an error even though everything succeeded. The right pattern is to accept the job, return a response immediately, and do the heavy work in the background. The caller gets instant feedback and the work still gets done. The difference is one parameter and one line. Look at the two versions. Without background tasks, the endpoint does all the slow work before returning. The caller waits the full 30 seconds. With background tasks, the endpoint reads the file, registers the slow work as a background task, and immediately returns a response. The caller gets their response right away. FastAPI then runs process_document after the response is sent, using the same server process. The caller sees processing instantly. The heavy work happens behind the scenes. That's the core pattern. FastAPI's background tasks is as simple as it gets. Declare it as a parameter in your endpoint and FastAPI injects it automatically. Call background_task.add_task with the function you want to run and any arguments it needs. Notice the status code is 202 accepted, not 200 OK. That's the correct HTTP status for I received your request and I'm working on it. The process_document function runs after the response is sent. It gets the file content, the user ID, and the vector store client, everything it needs to do the full ingestion without holding the connection open. Background task is great for lightweight post-response work, sending a notification, updating a counter, logging something, but it has real limits. If your server crashes while a task is running, the task is gone. There's no retry mechanism if the embedding API fails halfway through, and there's no way to check whether a task succeeded or failed. For heavy ingestion jobs, long-running agent workflows, or anything that needs to survive a server restart, you need a proper job queue. Celery with Redis is the most common Python choice. The job queue stores the task persistently, retries on failure, and lets you track job status. Use background tasks for simple fire and forget work. Use a job queue when durability and visibility matter. The job pattern is the professional version of background processing. Instead of just returning processing, you return a job ID. The caller stores that ID and polls a separate status endpoint to check on progress. Look at the two endpoints. Post/document/ingest creates a job, stores its status as pending, kicks off the background work, and returns the job ID immediately. Get/jobs/open brace job_ID close brace lets the caller check status at any time. The background task updates the job status as it progresses, from pending to processing to completed or failed. One important note. The in-memory jobs dictionary works for demonstration but not production. In production, store job state in Redis or a database so it survives server restarts. Quick recap. Never hold a slow HTTP connection open. Return immediately and continue work in the background. FastAPI's background tasks handle simple post-response work with no extra setup. For heavy long-running jobs, use a proper queue like Celery with Redis. And when callers need to track progress, use the job pattern. Return a job ID immediately and let them poll a status endpoint. Next up is logging and observability. How to trace what's happening inside Karan's API, catch provider errors, and keep visibility into your system in production. See you there. Hey, welcome back. Karan's API is now feature complete for Module 5, but there's one more thing every production system needs: visibility. When something goes wrong at 2 a.m., you need to know what happened, where it failed, and why. When your OpenAI bill spikes, you need to trace which endpoints are responsible. In this video, we cover logging and observability basics, structured logging, what to capture, and how to handle provider errors cleanly. AI backends fail in ways that are hard to detect without logging. An LLM API timeout looks like a slow response from the outside. A retrieval step returning low relevance chunks looks like a bad answer, but you can't tell if the model hallucinated or the retrieval failed. An embedding failure mid-ingestion means documents are silently missing from the knowledge base. Without logs, all of these require you to reproduce the problem from scratch. With structured logs, you can trace exactly what happened, which provider call failed, what the retrieval returned, and how long each step took. Observability is what turns a black box into a system you can actually operate. Plain text logs are readable by humans but hard to search programmatically. Structured JSON logs are readable by both. Every log entry is a JSON object with consistent fields: timestamp, level, message, and any extra context you add. Look at the JSON formatter. It takes a log record and serializes it as JSON. Any extra fields you attach to the log record get merged in automatically. Set this up once in your lifespan startup and every log call across your entire application produces clean, structured output. Most logging platforms, Datadog, CloudWatch, Grafana, Loki, ingest JSON logs natively and let you filter and alert on specific fields. Log at 4 points in every request. First, when the request arrives, capture who made it and what they asked for. Second, after retrieval, how many chunks came back and what were the relevant scores. Low scores are a signal that retrieval quality is poor. Third, after the LLM call, model used, token counts, and latency. This is your cost tracking data. Fourth, when the request completes, total end-to-end latency and final status. These 4 log entries give you a complete trace of every request. If a user reports a bad answer, you can pull up their user ID, find the relevant request, and see exactly what retrieval returned and what the LLM received. Provider errors need specific handling. OpenAI has distinct exception types: rate limit error when you've hit your quota, API timeout error when the call takes too long, and a general exception catch for everything else. Log each one specifically. A rate limit hit is different from a timeout. You want to be able to count each separately in your logging platform and alert on different thresholds. Notice the HTTP status codes too. Rate limit from OpenAI becomes a 429 to the caller. A timeout becomes a 504 gateway timeout. These are the semantically correct responses and they tell the caller exactly what happened and whether to retry. Good structured logs enable 4 things without any extra infrastructure. Debugging, search by user ID and session ID to pull up the full trace of any specific request. Performance monitoring, aggregate latency across all LLM calls and alert when average response time crosses a threshold. Cost tracking, sum token counts per user and calculate daily spend. Error alerting, count provider errors by type and trigger an alert when rate limit hits spike. All of this comes from the log fields you're already capturing. The logging platform does the aggregation. You just need to make sure the right fields are in every log entry. And the code we've covered in this video takes care of that. That's Module 5 done. Structured logs, 4 capture points per request. Specific provider error handling. That's all you need for a fully observable AI backend. In Module 6, we move into the first real project, building a complete RAG API for podcast transcripts. Everything from Module 1 through 5 comes together there. See you in Module 6. Hey, welcome to Module 6. This is where everything comes together. For the past 5 modules, Karan has been building the skills: endpoints, auth, state, background tasks, logging. Now he applies all of it to a real project, a RAG API for podcast transcripts. Users upload transcripts, ask questions, and get answers grounded in the actual content. In this video, we walk through the full system architecture before we build it. Let's get into it. Here's what the project does. A user uploads a podcast transcript, say a Lex Friedman episode. The API processes it, chunks it, generates embeddings, and indexes it in a vector store. The user can then ask questions. What did the guest say about AI safety? And get an answer grounded in that specific transcript. Each user has their own isolated collection. Their uploads don't mix with anyone else's. Auth protects every endpoint. Rate limiting keeps LLM costs predictable. Answers stream back token by token so the user doesn't stare at a blank screen. And every conversation is stored so users can follow up. This is a real product, not a tutorial exercise. Look at the architecture. FastAPI sits in the middle. It handles all incoming requests, runs auth and rate limiting, and routes to the right handler. Below it, two storage systems. PostgreSQL stores structured data, users, sessions, messages, and the operational metadata we log with every LLM call. Qdrant stores the vector embeddings for document retrieval. On the right, two AI services. OpenAI's embedding model converts text to vectors during ingestion and at query time. GPT-4o generates the final answer using the retrieved chunks as context. Every component from modules 1 through 5 is here. This is what they were building toward. Two flows to understand. Ingestion, the user uploads a transcript, FastAPI validates the file and checks auth, then kicks off a background task. That task chunks the document, generates embeddings, and indexes everything into Qdrant. The caller gets a job ID immediately and pulls a status endpoint to track progress. Query, the user sends a question with a session ID. FastAPI loads the recent conversation history from PostgreSQL, embeds the query, retrieves the top 5 relevant chunks from Qdrant, assembles the full prompt, calls GPT-4o, and streams the response back token by token. The exchange is then saved to PostgreSQL for future context. Clean separation between ingestion and retrieval. The architecture is clear. Two flows, ingestion and query, 5 components, FastAPI, PostgreSQL, Qdrant embeddings, and the LLM. Now we switch to the code editor and build every piece of this end to end. Let's go. Hey, welcome to Module 7. This is the second project. Karan's RAG API handles unstructured data, podcast transcripts, documents, free text. This project handles structured data. A user asks a question in plain English and the system generates and executes a SQL query against a real database. That's powerful and dangerous if you don't handle it carefully. Before we build anything, we need to understand exactly what the system can do, what it can't do, and where trust boundaries must be enforced. Let's walk through it. Here's the project. A user types a question in plain English. The system uses an LLM to generate a SQL query that answers it. That query is validated for safety, executed against a real database, and the results are returned. Optionally, the LLM summarizes the results back into natural language so the user doesn't have to read raw table data. Powerful, but the constraints are non-negotiable. Only select queries. The LLM gets the schema, not free access to the database. Every query is validated before execution. Result sets are bounded so one bad question can't dump an entire table. These aren't optional safeguards. They're the foundation of a trustworthy agentic system. Look at the architecture. FastAPI handles auth and input validation at the top. Below that, the orchestration layer. This is where the agentic behavior lives. A schema loader fetches the database structure so the LLM knows what tables and columns exist. The LLM generates a SQL query. A validator checks it. A safe executor runs it. Notice the clear separation between the orchestration layer and the storage layer. That line is the trust boundary. The LLM's output never reaches the database directly. Every query passes through validation first. The audit log records every query executed, who asked it, what SQL was generated, and what it returned. Trust boundaries are the most important design decision in an agentic system. Here's where they sit. The agent can generate select queries using the schema you give it. It can use joins, aggregation, sorting. It can summarize results. That's the full scope of its autonomy. What it cannot do is non-negotiable. No write operation, not ever, regardless of what the user asks. No access to tables outside the schema. No unbounded result sets, and no query that fails validation gets executed, full stop. Critically, these boundaries are enforced in code, not just in the system prompt. Telling an LLM only generate select queries is not enough. You validate the generated SQL before execution. The system prompt is guidance. The validator is the enforcer. The architecture is clear. Two flows, ingestion and query, 5 components, FastAPI, PostgreSQL, Qdrant, embeddings, and the LLM. Now we switch to the code editor and build every piece of this end to end. Let's go. Hey, welcome to Module 8. This is the final module, production readiness and deployment. Karan's API works on his laptop, but moving it to a server or sharing it with a teammate shouldn't require hours of setup. Containerization solves that. In this video, we write a Docker file for Karan's FastAPI backend and understand what makes a container build portable and repeatable. Let's get into it. Look at the left panel. 3 machines, 3 different Python versions. 3.11 on the dev laptop, 3.9 on staging, 3.8 on production. Different dependencies, different configs. Result at the bottom, hard to reproduce, prone to errors. Now, look at the right panel. One Docker container packages Python version, dependencies, config, and app code together. That same image runs on dev, staging, and production. All 3 green check marks. Identical, reliable, reproducible. Look at the flow. Developer writes a Docker file. Docker build turns it into an image. That image runs locally as a container. push it to Docker Hub and any machine can pull it. Look at the right side. The same image gets pulled into the staging environment and the test environment. Same image, different machines, identical behavior. Look at the Docker file. From Python 3.11-slim sets the base image. Slim variant keeps it small. Workdir/app sets where commands run inside the container. Notice the ordering. Requirements.txt is copied and installed before the application code is copied. This is deliberate. Docker caches each layer. If your code changes but requirements.txt doesn't, Docker reuses the cache dependency layer and only rebuilds the code layer. Flip the order and every code change triggers a full dependency reinstall. Expose 8000 documents the port, it does not publish it. That happens with -p at runtime. CMD starts uvicorn with --host 0.0.0.0. Without that flag, the app only listens inside the container and external traffic can't reach it. Two commands. Docker build -t rag -api :latest builds and tags the image. Docker run starts a container from it. Three flags to know. -p 8000 :8000 maps the container port to your host. Without this, the app is running but unreachable. -e injects individual environment variables at runtime. Never bake secrets into the image. And -env-file.env at the bottom is the cleaner option when you have many variables. Three things that matter specifically for containerized AI backends. First, never copy your .env file into the image. Add it to .docker ignore so it's excluded from the build context entirely. Secrets go in at runtime via environment variables or a secrets manager. Second, run as a non-root user inside the container. The default Docker user is root. That's a security risk. Two lines in the Docker file create and switch to an unprivileged user. Third, add a /health endpoint. Most cloud platforms and container orchestrators use health checks to know whether your container is ready to receive traffic. FastAPI makes this trivial. One endpoint that returns a 200 is all you need. Quick recap. Docker file is the recipe. Copy dependencies before code for faster rebuilds. Secrets go in at runtime, never in the image. Non-root user .docker ignore health check. In the next video, workers and concurrency. How many Uvicorn workers to run and how deployment decisions affect performance. See you there. Hey, welcome back. Karan's API is containerized. Now the question is how to actually run it in production. One process or many? How many workers? What happens to memory when you scale up? These decisions have real consequences for an AI backend. In this video, we break down how Uvicorn handles concurrency, when to add workers, and why memory trade-offs matter. Let's get into it. Look at the diagram. Three requests come in simultaneously. Request 1 goes to the LLM, request 2 to the database, request 3 to the vector store. All three are in the waiting state at the same time. The single Uvicorn event loop in the middle is handling all of them concurrently. This works because Karan's API is I/O bound. While request 1 is waiting on the LLM response, the event loop picks up request 2 and request 3. No request is blocking the others. Look at the two callouts at the bottom. Great for I/O bound work. CPU bound task blocks the loop. If one request runs heavy local inference and holds the CPU, every other request waits. That's the limitation. A single Uvicorn process uses one CPU core. To use multiple cores, you run Gunicorn as a process manager. Look at the Docker file CMD on the right. Instead of running Uvicorn directly, you now run Gunicorn with --worker-class uvicorn.workers.uvicorn-worker. Each worker is an independent process with its own event loop. Three benefits on the left. Uses multiple CPU cores, one crashed worker doesn't take down the API, more total concurrent requests handled. The rule at the bottom, start with 2 times your CPU count plus 1. 2-core instance gets 5 workers. 4-core instance gets 9. But for AI backends, this rule needs adjusting because of memory. Look at the diagram. The process manager spins up 4 workers. Each worker is completely independent. Look inside each one. Client, vector DB, SQLDB, config, and a model copy at 1 GB. Every worker loads its own full copy of the model. The math at the bottom. 4 workers times a 1 GB model equals 4 GB RAM. The warning, copies add up. The green callout. Small clients like the OpenAI HTTP client are fine. They're just lightweight wrappers. But a locally loaded embedding model gets fully duplicated across every worker. This is the trade-off that catches AI engineers by surprise on first deployment. Let's put numbers on this. Karan's API using OpenAI for embeddings is lightweight. Each worker uses around 150 megabytes. 4 workers on a 1 GB instance is completely fine. Now, look at the second table. A RAG API with a local embedding model loaded per worker. Each worker needs 1.2 GB. 4 workers need 4.8 GB of RAM. which means an 8 GB instance minimum. Doubling your workers from 2 to 4 doubles your instance cost. This is the memory trade-off. For API-based AI services like Karans, scale workers freely. For locally hosted models, minimize worker count and rely on async concurrency to handle concurrent requests within each worker instead. Look at the comparison table. Left column, I/O bound, calling OpenAI, Qdrant, PostgreSQL. Async handles concurrency within one worker. You need fewer workers. Scale by adding more async endpoints. Karan's RAG API with API-based models is exactly this. Right column, CPU bound, running local inference or embedding models. Async does not help here. The CPU stays busy regardless. You need more cores, or the better pattern is to separate model serving entirely. Run a dedicated inference server like Triton or VLLM and have FastAPI call it as an external API. That keeps the FastAPI layer I/O bound and the model server scales independently. The callout at the bottom says it cleanly. For hosted APIs, fewer workers and lean on async. For local models, separate the model server from the API layer. Look at the Docker file CMD on the right. This is the starting config for Karan's API. 4 flags to understand from the bullets on the left. Workers 2 for a 1 to 2 core instance. Adjust as you add cores. Timeout 120 because LLM calls can easily take 30 or more seconds. The default 30-second timeout will kill perfectly valid streaming requests. Dash dash keep alive 5 keeps connections alive for 5 seconds and reduces the overhead of re-establishing connections for frequent callers. Dash dash access dash log file dash sends access logs to stdout so your container logging infrastructure captures them automatically. Start here. Monitor real memory and CPU usage after deployment and let actual traffic data guide your next scaling decision. Quick recap. Uvicon's async event loop handles concurrent I/O bound requests efficiently in a single process. Add Gunicon workers to use multiple cores, but every worker duplicates memory. For Karan's API calling hosted OpenAI APIs, 2 workers on a small instance is the right starting point. Always set timeout to 120 for LLM workloads. In the next video, we deploy Karan's containerized API to the cloud. See you there. Hey, welcome back. The container is built, the workers are configured. Now we actually deploy. In this video, we look at 2 deployment options, Render for simplicity and Google Cloud Run for container native deployments. We also cover how to handle different configurations across dev, staging, and production without changing your code. Let's get into it. Look at the 3-row table. 3 options for a fast API AI backend. Render, fast setup, no DevOps experience needed, great for small to medium APIs. Trade-off, less control, scales less flexibly. Google Cloud Run, container native, scales to 0, pay per request. Trade-off, more setup, GCP knowledge needed. Railway. Similar developer experience to Render, but smaller ecosystem. The callout at the bottom says it clearly. Starting out, use Render or Cloud Run. At production scale, Cloud Run or another container orchestration platform. 4 steps on the left. Push to GitHub, create a web service on Render, connect the repo, set environment variables in the dashboard. Look at the start command on the right. It's the same Gunicon config from the last video with one change. Dash dash bind 0.0.0.0 colon dollar port instead of a hard-coded 8000. Render injects dollar port automatically and expects your app to bind to it. Hardcode 8000 and your service deploys but never receives traffic. The callout at the bottom, Render also auto-deploys on every push to main. Continuous deployment is built in from day 1. 5 steps on the right. Build and tag the image with the Google Container Registry path. Push it. Then before deploying, store your secrets in Google Secret Manager. 2 gcloud secrets create commands. One for OpenAI underscore API underscore key, one for API underscore key. Then deploy with gcloud run deploy. Passing dash dash set dash nv dash vars only for non-sensitive config, like environment equals production. For actual secrets, use dash dash set dash secrets to reference them by name from Secret Manager. This distinction matters. Set mvars values end up in your shell history and in the Cloud Run console in plain text. Anyone with console access can read them. Set secrets keeps the values encrypted and access controlled. Cloud Run injects the actual value at runtime. Step 5. Cloud Run returns a public HTTPS URL immediately. Second bullet on the left, Cloud Run scales to 0. No traffic, no running container, no cost. First request after idle takes slightly longer on a cold start, but for most AI backends, that trade-off is worth the cost savings. Same code base, different config per environment. Look at the settings class. Pydantic settings reads configuration in a specific order. Environment variables first, then the .env file. Locally, your .env file exists and pydantic-settings reads from it. In production, no .env file exists. The platform injects environment variables directly and pydantic-settings picks those up. No code change needed between environments. Look at the model_config line. It points to .env as the file. That's fine. If the file doesn't exist in production, it's silently ignored. The comment in the code makes this explicit. Env vars from the platform override the .env file. Below that, the conditional settings.environment equals production triggers strict keywords only https://app.karan.com. Otherwise, permissive for local dev. 3 files on the left. .env for local, .env.staging for staging, .env.production for production. The production one never gets committed to Git. Secrets stay in the platform's secret management. 5 checks all on screen as actual curl commands. Run these immediately after every deployment. Check 1. Curl/health. Expected. Open brace quote status quote colon quote OK quote close brace. If this fails, the app didn't start. Check logs first. Check 2. Read the startup logs. On render, that's the dashboard logs tab. On Cloud Run, it's gcloud logging read. A missing environment variable or failed database connection shows up here. Check 3. Hit a protected endpoint with no auth header. Expected 401 unauthorized. If you get a 200, auth is not running. Check 4. Send a real authenticated post to /ask with the API key header and a test prompt. Expected 200 with an answer. Check 5. Open /docs in your browser. Interactive documentation should load. If it doesn't, your app config has an issue. These 5 checks take 2 minutes and catch the most common deployment failures before users do. Quick recap. Render gets you live fastest. Connect your repo and set environment variables in the dashboard. Cloud Run gives you more control with container native deployment and scale to zero cost efficiency. Same Docker image runs everywhere. Only the environment variables change. And always run the 5 post-deployment checks before you call a deployment done. In the next video, we cover versioning, docs hygiene, and release readiness. What needs to be stable and clean before you hand your API to a front-end team or external clients? See you there. Hey, welcome back. Karan's API is deployed and running. But before he shares the URL with a front-end team or external clients, there's one more step. The API needs to be stable, well-documented, and consistent. A half-finished API handed to a front-end developer creates rework for everyone. In this video, we cover versioning, documentation hygiene, and the checklist Karan needs to clear before calling his API ready for consumers. Let's get into it. Look at the 2 panels. Left panel, unstable API. The connection between the API and the front end is broken. 4 problems listed. Routes renamed, fields changed, missing docs, inconsistent errors. The label at the bottom, downstream chaos. The front-end team builds their UI against your endpoint names and response shapes. You rename a field or change a route and their code breaks. You now have a debugging session and a frustrated teammate instead of progress. Right panel, release-ready API. Clean connection, green checkmark. Stable routes, clear docs, consistent schema, smooth integration. Label, reliable for clients. That's the goal. Get these 3 things right before you share the URL. Structure is stable enough to commit to. Docs are clear enough that consumers don't need to ask questions. Responses are consistent enough that the front end can write reliable code against them. Version your API from the start. Adding /v1/later is painful. URL versioning is the simplest approach. Look at the code on the right. The API router is created with prefix equals /v1/documents. Every route defined on that router automatically lives under /v1/documents/. In main.py at the bottom, routers are imported from routers.v1 and included. Result all endpoints sit at /v1/documents/ /v1/session/ and /v1/ask. 2 bullets on the left that define the rule. When do you introduce /v2/? Only for breaking changes, removing a field, renaming a route, changing a required parameter. Adding a new optional field or a new endpoint is non-breaking. It doesn't need a new version. When you do introduce /v2/, run both simultaneously during the transition so existing clients aren't forced to upgrade immediately. FastAPI generates /docs automatically, but its quality depends on what you put into your code. Look at the 2 panels. Left panel, 3 levels of metadata. The FastAPI constructor gets a title, description, and version. These appear at the top of /docs. The RAG query request model uses field with description and JSON_schema_extra on each field. that JSON underscore schema underscore extra equals open brace. Quote example, quote colon, quote, quote, close brace is the pedantic v2 way to attach examples. The older example equals directly inside field is deprecated in v2 and won't show up in docs correctly. Use JSON underscore schema underscore extra instead. When a developer opens /docs, they see real example values pre-filled in the input boxes instead of empty fields. Right panel, the endpoint decorator gets summary, description, and response underscore description. Now /docs reads like real API documentation. 15 minutes of work across your whole API, and your docs go from a list of routes to something actually useful. 3 rules all on screen as code. Look at each block. Rule 1, comment at the top. Stable field names never rename without versioning. The ask response model has answer, session underscore ID, and retrieved underscore chunks. The comment says, commit to this name. If you shipped /v1/ask returning answer, that field stays answer for the lifetime of v1. You can add new fields, you cannot remove or rename existing ones. Rule 2, consistent error shape across all endpoints. One error response model with error message and code. Define it once, use it everywhere. Frontends should not have to write different error handlers for different endpoints. Rule 3, no surprise nulls. Look at document response. The summary field is declared as optional stir equals none with the comment explicitly optional, not silently null. If a field can be absent, declare it. A front end expecting a string and getting null will crash. Explicit is always better than implicit. 5 sections, all on screen. Run through each one before you share the URL. API structure, all routes versioned under /v1/. Route names are final with no planned renames. Documentation, app has title, description, and version visible in /docs. All pedantic fields have descriptions and examples. All endpoints have summary and description. Consistency, all error responses use the same shape, no undocumented optional fields. Security, all non-public endpoints require authentication. CORS is configured for the correct front-end origins only. Operations, /health returns 200 and is monitored, logs are structured and captured by your logging infrastructure. This takes 30 minutes to clear and saves hours of back and forth with the front-end team. Karan checks every box. His API is ready. Quick recap, add /v1/versioning from the start. Fill out your field descriptions and endpoint summaries so /docs is actually useful. Keep response shapes consistent and document optional fields explicitly, and run the release readiness checklist before you share. In the final video, we wrap up the full course, connect both projects back to the patterns we've built, and look at where to go next. See you there. Hey, welcome to the final video. 8 modules, 2 complete projects, everything from writing your first endpoint to deploying a production AI API to the cloud. In this video, we close the loop on Karan's journey, map everything you built to patterns you can reuse, and talk about where to go from here. Let's wrap this up. Look at the before panel on the left. Karan built RAG apps but couldn't deploy them. That gap cost him the job. The rejected interview feedback is right there on screen. Now look at the after panel on the right. 3 things changed: production, FastAPI, auth testing, deployment, and the ability to ship real AI systems. He's not just an AI builder anymore. He's an AI engineer who can take something from prototype to production. And after completing this course, so are you. Look at the 6 layers on screen. These are not things you learned once. This is the toolkit you take into every AI backend project. Layer 01, foundation, type hints, pedantic models, async endpoints for I/O work, API router for scalable structure. Layer 02, dependencies, depends for shared logic, yield dependencies for setup and cleanup, dependency underscore overrides for clean testing. Layer 03, configuration, pedantic dash settings for validated config, lifespan for startup initialization. Layer 04, security, API keys for internal services, JWT for user identity and multi-tenancy, rate limiting for cost and abuse control. Layer 05, state, PostgreSQL for relational chat data, Quadrant for vector retrieval, memory patterns for conversation context. Layer 06, operations, structured logging, background tasks, Docker containerization, cloud deployment on render or cloud run. Pick any new AI backend project and this stack applies. The tools may differ, the patterns don't. Look at the 5 cards on screen. These are the mindset shifts that separate good AI backends from brittle ones. Designed for failure. Every external call can fail. The LLM, the vector store, the database. Catch it, log it specifically, and return the right status code. Never hardcode secrets. Environment variables, always. No exceptions. Async is not magic. Use it for I/O bound work. It does nothing for CPU bound work. Know the difference before you add workers or rewrite endpoints. Observability is not optional. If you can't see what your system is doing, you can't operate it. Structured logs, request tracing, token tracking from day one. Test error cases, not just happy paths. A system that fails gracefully is more valuable than one that only works when everything goes right. These habits outlast any specific framework or tool. That's a wrap. You came into this course knowing how to build AI applications. You're leaving it knowing how to ship them. Clean endpoints, solid auth, reliable tests, observable logs, containerized builds, cloud deployments. Everything Karan needed and everything you now have. The next time someone asks you, how would you serve this in production? You have a complete, honest, detailed answer. Go build something real with it. Thank you for being here and good luck.